We have a pretty decent amount of our basic game here figured out. We can kill enemies, enemies can damage us, we've got a lot of stuff going, but it still feels kinda stiff. And while a part of that is just the quality of the assets that we're making here, because we're going through everything relatively quickly, there's also not a lot of juice. So in this segment of the first game creation course, we're going to focus on adding that juice. And juice is just a catch-all term for everything that makes the game feel satisfying. So that can relate to things that just make it look fancy, or things that communicate something more obviously to the player. Today, let's take a look at two different types of camera shakes that we'll introduce, one for when we kill an enemy, and one for when we get damaged. I'll go into my tutorial folder, and just make a new folder for camera shakes. We'll get back to that in a moment. For now though, if I go into the player blueprint, we'll have some stuff going on there that we can hook into. That being the on event any damage. We run this subtract HP, and that's really all that it does right now. But we're going to add a little bit to this that's going to add a camera shake whenever we get damaged. That way, it is very obvious when we do and don't get damaged, aside from having to look directly at our HP bar. There's a bunch of ways that we can handle camera shake. We're going to do it the most basic and straightforward way, and that is with getting the player controller. And we can just, pulling over that, type in camera shake, and we can start a client-side camera shake. If we hook it up, we can put in a scale, whether or not it is on local, world, or a user-defined space. We're going to stick with camera local because that is the most straightforward. And we have a user space rotation. Again, we're going to ignore that for now. This sticks in a camera shake class, and we have a handful of different ones. The legacy camera shake, the default camera shake, and the camera shake base. If we just put in the default camera shake base and we get damaged, you will see that doesn't do anything. And that is because these are only templates. We need to make our own camera shake as a child of that template. These are just like a blueprint, like we've made before. If we go into a blueprint class, we can make child classes of so many different things. One of the things in this list is camera shakes. So let's go ahead and make one. That's why I made that folder before. And here we have the camera shake base, the default camera shake base, or the legacy camera shake base. We're going to go with the default camera shake base because the legacy is, well, mostly there to support other legacy systems, code that already exists that runs off of this. Take the default camera shake base. And we'll call this something like CS for camera shake, and then base damage. And double clicking that will open it up in a new window. And it has a blueprint graph here that we're not going to do anything with because this is not relevant. We can just close that altogether. The only thing that really matters is the details panel. And in there, we can choose whether or not this is a single instance or not, which means that whether or not they can restart or that they can stack. Difference isn't that big, especially if you aren't getting a lot of camera shakes in a very short period of time. Really what matters here is the root shake pattern. We can say a couple of different ones. We can make a composite, so that's a couple of different ones added together. A purlin noise camera shake pattern, which is a random noise pattern that does smoothly interpolate between values. So you can kind of imagine that what it does is it is a +1, let's say +1 to -1 scale. And it just says, okay, we have a random value here and a random value there. But instead of jumping from this value to this value like immediately, right, having it jump like this, it always smoothly goes from one value to the next random value. There's just spacing between those random values, essentially. A sequence camera shake pattern, which lets you animate a camera in a sequence and use that as a camera shake. That is very, very nice for very precise effects that you want to have. Or a wave oscillator, and that is literally just a sine curve that just oscillates with a certain magnitude like that. 9 times out of 10, you're going to want to use just a purlin noise, and that is plenty fine. We can shake a couple different properties, that being location, where is it within the world, and individually influence the amplitude, how far does it move, and the frequency, how fast does it move of that amount. for either the location as a whole, X, Y, and Z, or individually X amplitude or frequency, Y amplitude frequency, Z amplitude frequency. These are the kind of things that you just kind of plug some numbers into, see what it feels like, and start tweaking. Maybe I wanted to move more. More doesn't look good. Maybe I wanted to move faster. That doesn't look good either. Maybe I wanted to move just a little bit, but very fast, or very slowly, but very far. And you just tweak these two numbers together until you get something that you like. And we have the same thing here for the rotation and the field of view. We're going to leave field of view alone for right now. Rotation might be kind of nice to work with. We have the pitch, the yaw, and the roll. So if you imagine this to be a head, pitch is nose up and down, roll is the head tilting side to side, and yaw is looking left and right to either side. That means that maybe we want to add a little bit of roll in here, but no yaw and no pitch. So we're going to set the amplitude for yaw and pitch to 0. And I'm just going to add a little bit of roll at a amplitude of, let's say, 15. Again, this might be a thing that's just going to look really bad. We'll have to see what it looks like in practice. Then we have the timing. How long does this camera shake take? How much does it blend in? And how much does it blend out? So we can imagine that this camera shake does this amount of transformation to any property of our camera. And that works if our 0 line of it not shaking at all exists here, because then it can just start from where it is at and do the thing. But what if our 0 line exists here and it starts at a shake value of 0.5 or 0.7, something along those lines? Then we're going to have a bit of a jump cut into it snapping to this value. So this blending just blends over a certain period of time from our 0 value into the start of our shake. Then at 0.2 seconds or whatever we put in here, it's going to entirely just do the value of those shakes. And then at the end, it's going to interpolate all the way back to whatever our non-shaking, like our 0 value is, essentially. And that takes however long this value is given in. 1 second might be a little long, so let's go with 0.5 seconds and then have our blend in and out only be 0.1 second. This is our first try at making this basic damage thing. Then going back into the character here, we can now choose our camera shake, basic damage, and let's just see what that looks like. We can find our enemy here and get hit by them, and now our camera shakes a little bit when we get hit. There's much more of an obvious tell that we're getting hit because the camera shake is harder to ignore than just our HP going a little bit down. And if we want to use these same values, but just make everything a little bit larger and a little bit faster, we can just set the scale here to 2. And that will just make everything in here just multiply by 2. And that will look a little something like this. It's probably going to be a bit much in this case. Again, this is the kind of thing where we really try to excel at the art of pulling numbers out of thin air and just kind of seeing if they work. This might still be a little intense, to be honest with you. And I think this is a pretty decent I got damaged kind of camera shake. Fantastic. That's one camera shake. But now, what if we want a different camera shake for when the enemy gets killed? Because you want that to be something visually different to differentiate easily for the player between hitting something or getting hit. Those shouldn't exactly be the same effect, right? So for that, let's just go back to our basic damage here. Press this browse to asset so that we open up the folder that exists in. And I'm just going to Control and D to duplicate it. Camera shake underscore kill enemy. And for this one, I'm just going to reset everything real quick because I'm not going to use any of the normal location stuff. I don't want to change the X or the Y. I only want this to shake a little bit up and down. So the amplitude for X and Y is at 0. The amplitude for Z, let's set this to 10. And then maybe a frequency of 2. And what I most want to do is I want to change the field of view. This is something that you want to be careful about, because it is a recipe to introducing motion sickness, and you want to avoid that if at all possible. But doing this a little bit and subtly can be a pretty nice effect. So let's say 10 degrees with a very, very low frequency. And instead of doing this as a pure noise, I'm going to do this as a wave oscillator. So it just goes up and down smoothly without any randomness to it. And personally, I've forgotten where exactly I put the base enemy because it's been a while since I've personally opened up this project. So I've opened up BP enemy 1, and then we can see the parent class of it is BP base enemy. If we just click on this open parent in editor button, it will just open up our base enemy blueprint. And where actually was it? It was just in AI. That makes sense. And we can get right into editing the blueprint for this. So when the enemy dies, we have this on overlap. If it is a character and it is moving down, we do on enemy kill response. Probably not a bad idea to put it in here so that we can individually decide if other child blueprints that we made off of this will or will not inherit this same behavior. So we're going to just do that right here. We can, again, just get the player controller. This is just as easy as that. And we can start camera shake on client again. And for this one, we're going to just start the camera shake for kill enemy. And as easily as that, we've now got a different camera shake when we kill the enemy. Let's take a look at if that works. It's a very subtle one. After changing to the wave oscillator pattern, it seems like a lot of my settings here got changed. That's on me. That will happen, right? Because when we go back to pure noise, you can see that it has some different properties that it kind of spawns in when we change over to wave oscillator. Mainly that being the initial offset type. Where do we start off? Do we start at any random point in our up and down curve? Or do we just start at 0? And in this case, we're just going to be, well, starting at 0. So we set this amplitude to, again, let's say 15 maybe. And we start this at 0. And then for our field of view, I think I set this to 10. And we also start this at 0. And give it another shot. Let's see what this shake looks like now when we jump onto the enemy. We can see it does a little wiggle in our field of view. There's a little bit in the position. The position probably could stand to being a little bit more extreme. So let's go up to, I don't know. So let's do a last one where we duplicate this again with Control D, and we'll call this kill enemy animated. And for this one, you can maybe imagine what we're going to do. We're going to use a sequence camera animation instead. And this takes a play rate, a scale, a blend in time, a blend out time, and whether or not it takes a random segment, and if so, how long that random segment will be. But we're just going to use the entire sequence, and we'll make a animation sequence to fill in here. I'm going to put this in camera shakes, and let's call this CSA, camera shake animated, enemy killed. Something simple and straightforward like that. If we open it up, we will be able to see it spawns in a cinema camera actor for us, which should be at location 000. And it will just do whatever we animate here relative to wherever our camera is in the world. It's not going to snap to 000 or anything. So let's animate the transform for it. And I'm going to add a keyframe here at the very start. Then this is a 30 FPS timeline. So let's say at about 20 frames. I want to move up the camera a little bit and maybe even tilt it up slightly. Set a different keyframe again. Then we hold that for a handful of frames, let's say until frame 30. And then go into frame 45, making this about a 1.5 seconds long animation. I'm going to paste that back in. It's a little annoying to animate this because 000 in this level obviously is inside of a block of a static mesh, which makes it annoying to see what is actually happening with any of this. But let's just see if we close out of this, we save everything, what that's going to look like. We'll go into our BP base enemy and use our, oh, I just called it CS, not CSA. Well, anyway, the enemy killed animated, and see what that looks like. It's a little much, maybe, but you can see it does do the exact thing that we animated it to do, which now is easily changeable. If I open this back up again and I go back into here, transform, and I say, well, I want this to also maybe kind of does a orbit around. This is probably going to look pretty ugly, but I'm just trying to show this and make a point of you can make this do whatever you want. As you can see, yeah, that didn't work very well at all, because what it is doing, it's not actually orbiting around the player. It is orbiting around where the camera's original position is. So what it is doing is it's orbiting around here instead of orbiting around here, which is probably what you would want. But that's the basics of camera shakes. You can go really wild with this, and just adding some camera shakes in response to actions, even if it's just a little bit, really makes it feel much more impactful whatever is happening in your game. Be it getting damaged, dealing damage, or even if you're making a survival game. If you're swinging your axe at a tree, on impact, add a little bit of a camera shake, and will sell the impact of that swing just so much more immediately. We've added a little bit of feedback into our game in the form of these camera shakes, but today let's dive one step deeper and add some basic particles to, again, hitting enemies and getting hit by enemies. Setting it up is going to be relatively simple. We'll just make a new folder to house all that stuff in, call that something like FX for, well, effects. And in here, we can make a new Niagara system directly, but let's talk a little bit about Niagara, because Niagara is the most used particle system in Unreal. There's also Cascade, but that's for the most part just an old system. You might run into some marketplace assets on Fab that use Cascade, but for the most part you're going to be using Niagara going forward. And Niagara has a concept of a system, which is a completed particle effect, and singular emitters that are the rules of how specific types of particles should behave. So instead of just making a system directly, if we scroll down into effects, there we can see we can either make a emitter or a system. A system is just a combination of emitters. I'm going to make a system first, then we're going to take a step back into making an emitter, and then we're going to go through and add that emitter into the system. So if we make a Niagara system here, we have a couple of emitters that we can start adding in as a default. So a very common one would obviously be completely empty. You need to do everything there entirely by yourself. A fountain, which is an infinite spawner of particles that just keeps on going and keeps on going. Or the omnidirectional burst, which will spawn in a bunch of particles that just fly out in all types of random directions. Let's just create one with that as the base here, and we'll call that FX enemy death. Let's say this is going to spawn in when, well, the enemy dies. Opening it up, we can see this interface here. It's a little bit cramped because my UI scaling is a little bit bigger, because of the fact that I'm making this into a video. I want everything to be very easily seeable. I'm going to set this back down to 1.5 for now, so that just a little bit more of this fits on screen. Over here at the left hand side, we have a preview of the particle system. At the bottom here, we have a timeline for that preview. As you can see, I can scrub back and forth, and it simulates it either forward or backward. And in here we have all of the system. It has a little system node here. And this node is just all of the settings for the system itself. How should it loop? Should it loop infinitely or once or just multiple times? How long is one loop considered to be? And you can run some code on when a system spawns or when a system updates. This is essentially just the begin play or the event tick of the system as a whole. The system doesn't do anything in terms of spawning in particles though. That's the individual emitters. We started off here with a omnidirectional burst emitter, and that has a bunch of these little modules that decide how the particles in them both behave and look. So here as well, we have this split up in a couple of different things. When the emitter initially spawns in, we can add in some modules to do stuff. If you want to have the emitter have a variable to itself, for instance, you could set that up here. You would make a new parameter, as it's called then. So set new or existing parameter directly. There we can just add a new parameter. We make a new, let's say just a float. You can look for a whole bunch of different types. Again, essentially the same thing as a variable in Blueprint. You make that, and now that is a float variable that exists in the context of just this emitter. As long as this emitter exists, it's going to have this float value, let's say 80, and we can make this the spawn rate or something like that. All this other stuff can then use this emitter value, and it's only going to affect things within this emitter. That's something that you would maybe do on emitter spawn. Emitter updates just happens every frame for this emitter, and in this case, that would be update the emitter state, where we can set a bunch of stuff as well, whether or not its lifecycle is individual to itself or exactly the same as is set up in the system, if it should loop infinitely, once, multiple times, how long the loop duration is, all that type of stuff. Next up, we have a spawn burst instantaneous. This is where the particles actually spawn in. It checks this emitter updates every frame, but spawn burst instantaneous will only happen by default at the start of whatever this emitter gets spawned in. You can change that by changing, for instance, the spawn time to 1. And you will see that this keyframe looking thing down here will move in correspondence to me changing that value. So if I want the particle system itself to spawn and maybe start spawning from a different emitter, but this omnidirectional burst specifically only needs to spawn in half a second later, I can say, okay, this burst spawns in at 0.5 seconds. So we can do this, and then at 0.5 seconds, it will spawn in. I can make this same emitter spawn in multiple times. So if I go in here and I add another spawn burst instantaneous, you can see I now have 2 of these keyframe things, which means that once at time 0 is going to be spawning them in, and its spawn count here is set to 1, where the spawn count there is set to 100. So at the start, it will spawn 1, and then at half a second later, it'll spawn 100, and that's going to now be the loop. And the wonderful thing about that is that because it's just using the same emitter twice here, if I change anything down here about how the particles behave or how they look, it still is the same emitter that's just emitting twice. Matter of fact, we can also add a spawn rate. And instead of just spawning at a given time, this will just always spawn a X amount of particles per second. So if we add in a spawn rate and I say, well, I want to spawn in 15 particles per second, then as long as this block down here in the timeline exists, it's constantly going to be spawning in about 15 particles per second. Let's make that more like 50 maybe. And then adding back in these 2 spawn bursts instantaneous, you see it spawns in spawn rate, it's all good, it's all good. And then when the loop resets here in a moment, you'll be able to see that it starts out with those 2 bursts and then still has the spawn rate going over top of all that. All that is confined within this one emitter. All these particles behave exactly the same way, they just get spawned in a handful of different ways. Usually you wouldn't have a spawn rate and spawn bursts within the same emitter. You can, for very specific situations, it might make sense. Generally speaking, you have an emitter that either is responsible for spawning something at a different rate, or any of the other given spawning mechanics that we have. We have things that spawn in particles every X distance as the emitter moves. We have things that spawn things in a grid. These are the 2 most common. Usually your emitter will have one type of spawner that it uses. And then it can have multiple of that type, like multiple bursts or even multiple spawn rates. But it's not often that you would see those combined within one emitter, even though it is technically entirely possible to do so. So I'm going to get rid of the spawn rate for now. And I will move this spawn time to 1.5 seconds just to make a little bit more distance between the 2 bursts. Then we move on to particle spawn. This is everything that happens for every individual particle that we'll see in here. So far we've been talking about the emitter as a whole. So emitter spawn, what happens when the emitter itself is spawned in. Emitter update, the things that the emitter is responsible for doing, every update loop. Now we're starting to talk about the individual particles. So almost always on particle spawn, you want to initialize the particle and give in a whole bunch of data about it. What is the minimum lifetime or the maximum lifetime? You can set it to just a direct value as well. or random. Usually it has some amount of randomness in there. And this is just how long does the particle exist. What color is the particle? We can set this to pink, and you can see now the particles all spawn in as pink. Now blue, green, yellow, whatever you want to do. Let's go for a maybe slightly bluish, but mostly still white type of color. We have some attributes for the sprite, mesh, or ribbon. This hooks into the renderer all the way down here. A lot of your effects are going to be based on sprites, most likely. Some about meshes. But this is setting the size of your particles for the most part. So if I set the uniform size here to 15 and 25 instead, it's going to have a random size that is uniform. So it's not going to be stretched or squashed in weird ways. That's going to be between 15 times the base scale or 25 times the base scale. If you want that to be a wider margin, you can set this to 5 to 50 maybe. And you can see now there is a much larger difference between the smallest particle and the biggest particle as they spawn in. And you can do the same thing with the mesh scale as well. These are distinctly different attributes. It's not just a single size attribute that applies both to sprites and meshes. So if you're trying to make a particle effect and change the sprite size, and then at a later date you're like, let's move to using a mesh for this instead for whatever reason, you will need to replace everything that influences that sprite size with using a mesh size instead. We tell them where to initially spawn as a particle. So a shape location is oftentimes what we will use. There is, again, you can spawn them in a grid or whatever, but a shape location just lets you put in a primitive shape, be it a sphere, a cylinder, a box, a torus, a cone, whatever. And each one of these has its own properties that you can play with. I'm going to stick with sphere for now. And we can set the sphere radius to either just 0, which spawns them all at a point, or maybe 1, which spawns them at a very, very small sphere, or 100, which spawns them all initially relatively far away. These particles, when they spawn in, get given an initial velocity. In this case, we set that velocity from a point, and that point is just 0, 0, 0. We make the particles shoot away from that point. We also can give them velocity in a cone, which all makes them shoot into a given direction instead. Or just a linear velocity, which all makes them move in the same direction. So let's say that we want to give them 500 units of upward momentum. They all just shoot up, and then gravity, which we'll get to in a moment here, will take them back down. From point is a pretty good one, so we're going to stick with that for now. All of this works on every particle individually, and there is a lot of them. So as this becomes more and more complex, it might become relatively expensive to do this with thousands or tens of thousands of particles. So it oftentimes is a good idea if you find yourself with a particle effect that doesn't really feel like full enough or powerful enough. Instead of just cranking up the amount of particles that you're spawning in, try to see if maybe making the particles bigger in initialized particle does something as well. Because if you can make your particles bigger and maybe use a bit of clever shader stuff, making a material for your particle to give it more detail, it can greatly reduce the amount of calculations that are needed to do in particle spawn and specifically particle updates. Because if it needs to do a bunch of gravity calculations on 100 particles versus 10,000 particles, obviously you want that number to be as low as possible. Unreal is able to handle a pretty decent amount of particles, but it's got its limits. If you do need an insane amount of particles, you can come up here into the properties and change this from a CPU simulation, which is good at being very accurate, but not good at doing a massive amount of individual particles, to a GPU simulation. This one is a little trickier because it relies on the bounds of your particle system to decide whether or not it should render at all. So there's a higher chance that your particles just suddenly disappear. Doing collision with GPU simulation, for instance, is a little bit more tricky because it doesn't have access to a bunch of the collision data that the CPU would. Hopefully we're kind of keeping up and getting through all this, I'm going to speedrun this particle update because at this point, I guess you kind of get the point of how we're walking through this. So we do the particle state every update, and this mostly is just checking if the particle's lifetime, which we set up in initialize particle, has run out or not. And if it has, it will automatically just kill the particle. We have a gravity force, which I hope is fairly self-explanatory. Drag, that'll slow down particles as they're moving. You'll be able to see if I disable gravity real quick. We don't have any gravity, but it still slows the particles down as they move from their initial velocity. If I also don't have drag, you can see that they just linearly keep moving at the same speed. So there's a kind of a curve that exists between the velocity that you add to a particle and the amount of drag that a particle has. We can scale the sprite size. This is a thing that you're going to do very often, is scale something over a certain period of time. And usually that period of time is the normalized age of the particle. What that means is we have a 0 to 1 graph here, 0 being the start of the particle's lifetime and 1 being the end. No matter how long the particle lives, this is not just 1 second. If the particle lives for 10 seconds, that means that 0 is, well, 0 seconds and 1 represents 10 seconds. So this keyframe here that exists at a time of 0.695 would be after about 6.9 seconds, almost 7 seconds. However, if that particle exists for 100 seconds, that would be about 69 nice seconds instead. This is just a proportional view of how, in this case, the particle size changes as the particle lives longer. It will have a value of about 1 at the start, so just its normal size, and it will keep that for a pretty long period of time, and then toward the end of its lifetime, the last 20% or so, it slowly goes down to a value of what should be just 0, so that they do this little shrinking toward the end, and they just don't pop out of existence. If we didn't do that, and we also can scale the color in the same way, you will see that the particles just spawn in, stay the same size that they are, and just kind of pop out of existence. Doesn't look very good. So we both scale the size down as they get closer to their death, and in this case we also scale the color, and specifically the alpha, so the transparency of the particle, to also go down as the particle ages towards its end. Finally, we pretty much always add in a solve forces and velocity, and that just takes in, okay, what forces are being applied to this particle, what is its current velocity, and how does that mean it should move. In Particle Update, we also can continuously add in extra forces. Generally, what we do is in Particle Spawn, we add velocity, and in Particle Update, we add a force. This sets it more or less directly to what it should be at the start of its lifetime as it spawns in. This is applying forces that then change that velocity, that being either drag, slowing it down, or we can see if we just set some force, the gravity force. It's a force that applies downward velocity continuously, making it fall faster and faster and faster and faster. We can limit the amount of force that we add to it. We can add some simple linear force. So let's say that we add some of that, and we want to add a bit of force into the X. You will see that now it moves a little bit toward the left here at the start of the lifetime, and then starts moving quicker and quicker the longer that the particles live. Because at the lifetime of these particles, instead of like 10 to 15 seconds, you will see that they start speeding up more and more as they get more of that velocity applied to them. And the drag is kind of slowing that down, but especially if I get rid of the drag, you'll be able to see that that increase in speed really exists. I'm going to delete that linear force again, and I'm going to delete the gravity force in this case as well. I don't really need the gravity force. And we'll set this back to 1 to 1.5 seconds instead. That is one singular emitter that we just went through, and you can add a bunch of emitters into a system that spawns in. Individual emitters can't be placed into the world. If we make a emitter as well, so let's go FX Niagara emitter, and we'll just base this on a completely empty one, and usually we call these NE for Niagara emitter, And let's call this landing dust. We'll spawn this in when we land on the ground. You'll see that if I try to pull this into the world, I cannot do that. However, with a system, I can, and it will let me, and it will display it in the world, and that is entirely fine. The only use for emitters is to be placed inside of systems. So we open up this one again, and I just pull up my content browser here. I can just drag this in here, and it will add it in, no problem. Let's do something fun and quick with this landing dust emitter real quick. It's entirely empty, so we need to set everything up from nothing. We can use this one for reference. We need to add in an emitter state and then some spawning, then initialize the particle, and we'll get into the sprite renderer and mesh renderers probably a little later. For now, mostly everything is just going to use the default sprite material. So let's start with that. Emitter updates. We add the emitter state. On particle spawn, we initialize the particle, so we can just type init part, and that should get us initialize particle. The renderer, again, there is a whole bunch of different ones. We can render them as light sources, as decals, as components. There's a bunch of different interesting stuff that we can do. For now, we're going to stick with the sprite renderer, and we'll just spawn in a handful of particles that just kind of blow away from a central point. In emitter update, we'll spawn a burst instantaneous. I don't know, let's say we want to spawn in 50, but maybe we don't want to spawn in 50. Maybe we want to spawn in a variable amount, right? We don't really know how many of these we want to spawn in. Maybe sometimes when we use this emitter, we want to spawn in 50. Sometimes maybe 10, sometimes maybe 100. For that, we need to make a parameter out of it. And for systems, you can make user parameters. We'll take a look at that in a moment. But for individual emitters, that's where we get this emitter spawn. What I just showed you before, we can make a new or existing parameter, and we'll just make a new one. In this case, it's going to be a integer, so it'll be a integer 32. Then if we apply that and save it real quick, going over to wherever we use it, we can now see that we have this as a individual value that we can change. If we have multiple different ones of these emitters within one system, this one can be given a different value. So let's say that this one spawns in 250 and this one spawns in 150 instead. Then we spawn in particle, we'll spawn it in at a shape location. So we just type in shape location and we can spawn this in a sphere, that's fine. But what I'm going to do instead is I'm going to spawn them in a ring or in a torus. The torus is a three-dimensional shape, it's a donut, and it's going to be spawning either on the surface of that donut or in the volume of that donut. A ring or a disk is just the two-dimensional version of it, which just spawns it on a 2D surface, or in the case of what I want to do with it, just on the edges. However, we're still only spawning in one particle, as you can see, and that's maybe not ideal. And that is because I never hooked up the spawn count in Spawn Burst Instantaneous to this emitter parameter that we made. So let's do that. In spawn counts, we can just click on this little drop-down menu. And if we look for the emitter value that we made, which we probably should give a name, just click on it and rename. Let's call this spawn count. We can just find that based on the name. And you can see here we have spawn count, both its current value and its initial value. The wonderful thing about these parameters is that they are just variables. So if we do want to do anything to change them in either particle spawn or particle update, we can, but the emitter is going to remember the initial value of it as well, which could be useful if you want to see the difference between its current value and its initial value. I'm going to set it to spawn count, and now it spawns in a whole bunch of them in, well, a ring. Initialize particle, we'll set this to be a random duration of 0.7 to, I don't know, 1.2 seconds of lifetime. And we'll give it some random velocity. So we add velocity to this, and you immediately see, okay, it's going to scream at me because it has issues, because I'm trying to add velocity, but it doesn't know how to solve for that velocity. And do I need to add something? I forgot what I need to add. And don't worry, it's just going to give you these fix issue things, and it just adds all the modules that you need. In my case, I'm going to give these linear velocity. What I'm going to do is I want to give this a random value in the x and the y, but no value in the z. So I can make a vector here, make a XYZ combination out of 3 separate floats. And you can just do that by make vector. And that's going to give me individual access to the X, the Y, and the Z. Now I can go one step deeper and set up how I want these X, Y, and Z values to be generated. In my case, I just want that to be a random value in a certain range. And that's going to be a -1 to +1 range. I'm going to do that for both the X and also then for the Y. And that almost does nothing because they now have a velocity between -1 and +1, but only at a scale of 1. And instead of setting this to maybe -100 to +100, which would be kind of weird and annoying to do, we can just keep it at a normalized value for the directions and then increase the scale as a whole to 500. And there you can see now they spawn in and all go into a, well, random direction. That said, in this case, maybe just a velocity from point makes a little bit more sense. So let's give this maybe velocity of 100, maybe even 250, something like that. Because we want to make something that happens when we land on the ground. And here we get into the balance of velocity and drag. Because now in particle update, I'm going to be adding in drag of my own. And that is split into rotational drag and positional drag. And you can see that it doesn't really go as far. So I go back into velocity and say, well, maybe I want this to be like 800 in velocity. And that is way too much suddenly, right? Going back into drag, setting this to 2, we get a very powerful initial impulse, but then also it doesn't travel too far. I also do think that they still, well, I messed up a little bit with the maximum lifetime here. They still are maybe a little too long living. So let's set this to 0.3 to 0.5 maybe. And then they die out at a decent time. No, they don't, because we forget one important thing here, and that is this particle state in the particle update. So we need to add that because otherwise the particles don't die at the end of their lifetime. Now, let's see how long do they live with this. It's a bit short. I think the 0.7 to 1.2 that I had initially as a guess was pretty good, probably. I think that's pretty good. But now we get into the issue where, hey, they just pop out of existence, the thing that I showed before. And for that, we'll just scale the color of our particle. And we want to scale the RGB and the alpha separately in this case. Because we're going to keep the RGB, the actual color, alone. The only thing that we want to scale is the alpha, how much we can see through them. And if we get a float from curve, by default, it's just going to have a curve that goes from fully opaque to fully transparent. It's got a couple other pre-existing curve profiles that we can use. Linear for a long time and then slowly fading off toward the end, which might work a little bit better for what we're doing here. But I think what we might like to do is do something a little bit like this. Just take the linear going down and then right click this and set this to being user interpolated so that we can just make this a bit of a curve. And you see that it fades out relatively like smoothly and nicely now. If we also then add in a scale sprite size, instead of what we did before with the spawn burst instantaneous where they just also become smaller as they get closer to despawning, what I'm going to do here, I'm going to start them out at time 0 at a value of 1. They're going to be their normal size when they spawn in. Then at the end of their lifetime, they're going to be, let's say, 3 times their size. And that'll be roughly the base of how we're going to work with this. And they don't show up at all now, and that's because we've never set the sprite size itself. So now that we're trying to change an attribute that wasn't assigned at all, it kind of freaks out and it just, everything is zeroed out. You need to make sure that in initialize particle, scales the sprite size mode is set to one of these. I hope that most of these are pretty self-explanatory. You've got uniform, which is not stretched or squashed. Random uniform, which is a random size, and that's going to be the one that we use here. and the one that we've seen before that has no stretching or squashing. Non-uniform and random non-uniform are just the counterparts to those, where we can give in a X size and a Y size individually so that they can be a little stretched or squashed, and there can be some randomness in how stretched and squashed they are as well. Just going to stick with random uniform here, and let's say that they are 20 to 35 units in size by default. They'll be growing larger and less opaque, which kind of gets the feeling across of this being a cloud of dust that is being blown out. Maybe even like 35 to 50, honestly. And if we update the ring radius to start maybe being a little bit smaller, without even doing anything, introducing unique sprites, introducing unique materials, which we'll look at in the future, no doubt, we already have a little like dust cloud effects that we can use now. Last important thing to add for dust though is this just moves laterally at the moment, and that's fine. But if a dust cloud is getting kicked up, well, it's getting usually kicked up, right? So for that, let's add in a bit of that, and we're going to just use a gravity force for that. And instead of the gravity force going downward, as you would expect here, we're just going to invert the gravity, and it's going to go upward. This is a little too strong, maybe only 250, but the wonderful thing about a gravity force is that it is more or less a linear force that is intended to be used more exponentially like this. And now we've got our very basic like landing dust system. And as we can see in our enemy death, which is a weird thing to have this exist in, but we've got two of these systems which are now fully built out. Everything that we did here is now reflected in the emitters that we added into that other system, and it's got two of them. One of them that's got a spawn count. The second one is a little messed up because we added, or changed rather, this parameter's name after we've already introduced it into a system, which sometimes is a little like messed up and weird. So we just copy it over again, and now we can see we've got a spawn count. One of them is a dust cloud that spawns in 150 particles when it gets run, and the other one runs 250 instead. So we just set this spawn burst instantaneous here to the spawn time for, I don't know, 3 seconds on this one. Let me make sure that the particle system actually lets it exist for that long as well. And we just disable the omnidirectional burst for now. We will see that they start just kind of spamming themselves, even though that doesn't really make sense. And that is because if we click on either of these, we can see somewhere in here, probably in the emitter states, they are taking their life cycle mode from the system. So they're using the same thing that the system itself has set up, and that is infinite looping. So instead we can set this to using its own life cycle mode, and there we can set it to only looping once, which is to say that this emitter is going to run once for every loop of the system as a whole. What you can imagine this to be like is we've got our system, and that system has a whole bunch of emitters in it. This system has a loop time, let's call this LP, of 10 seconds. So everything that it is programmed to do, it's going to do that every 10 seconds. That means that even if these things are set to only looping once, the system itself will trigger these to just run once every 10 seconds. But within that system, let's say that this emitter has a loop time of 3 seconds, and it's set to loop 2 times, right? That would mean that every 10 seconds, when this emitter gets told, you do your thing, it's going to loop at a duration of 3 seconds, and it's going to go through, let's say, 2 times, or only once, or for the duration of the entire system loop. Then this emitter could have a loop time of only 1 second, while this emitter has a loop time of 6 seconds, which doesn't make a lot of sense within the loop of the system as a whole. But all these can be working on different loops. Just because this thing is set to looping only once doesn't mean that it's only actually going to run once. It's going to run once per loop of the system as a whole, which we can see by just going into both of these, setting these to just loop once. And now you'll see it runs once. And now the other one ran at 3 seconds. That is exactly what I told it to do. And then it does it exactly that same way when the system as a whole completes its loop and starts its loop over again. For this lending dust, it probably makes sense to set that emitter state within the emitter itself to being, well, self and once, instead of having to do it on a per individual system. All right, that all out of the way, we've been mixing these two emitters into this one system. That doesn't make a whole lot of sense, of course. You can just right-click on any given emitter and create a system out of it. And that then creates it with the same name, but just with system after it. Generally, I think most people use NE for Niagara emitter and NS for Niagara system instead. But now we've got that system with, well, that one emitter in it. It's a very simple emitter, but we can very easily now copy this over and say, well, I want this one to just spawn time a little bit later, maybe at 0.2 seconds. So we've got a little double thing here, maybe just 0.1 seconds. And I want the spawn count to be a little bit lower. This is only about 50. And if we start introducing other parameters into this, maybe the size, I can very much imagine that this size may be something that we want to parameterize. So we, in our emitter spawn, add in a new float parameter and call this size. Let's set that by default to 40. And then when we initialize the particle, we use that size that we made it as an emitter parameter. And then for the max sprite size, maybe we just add two floats together, and that will be our size. And then a multiply floats. And this starts being kind of hard to read relatively quickly, and we'll probably get into some more manageable ways to do anything that's got more than 1 or 2 steps worth of adding or subtracting or doing any type of math, because this becomes really messy really quickly. But what I want to do here is just, for our max sprite size, I'm going to take our base size and then add to that about 10% of that same value. So that way we still have some amount of variability within about a 10% range. We also might want to set up our color as a parameter. So let's add a color. We can just add a linear color here, and let's give that a name. You can just click and press F2 to rename things, and just call that particle color. And when we initialize the particle, we'll use our particle color for that. And now that we've done all those things, these are now all adjustable on a per emitter basis. So this second one, maybe we want the particles to be a fair bit smaller, but we want them to be maybe a little bit more blue. That's kind of hard to see in this case, so let's maybe make them bigger instead. And you can see that the second wave there just adds a touch of like a little bit of blue in there, and maybe they're a little bit less bright as well. And now we've got one system with 2 variations of the same emitter, just doing slightly different stuff. Of course, you can set this up to then also have different lifetimes, and you can parameterize everything you want. The last thing that I want to take a look at is taking the parameters one step further and parameterizing the system as a whole. Because now that we're in a system and no longer in a emitter, we can make user parameters. And these are pretty much the same thing that we're seeing up here in emitter spawn, but instead they exist for the whole system, and they will be editable on a per instance basis when you put these into the world or put these into a blueprint, or you'll see in a moment. As a super simple example, I'm going to just make a parameter for the size. So we can just go in here, use a parameter, add a new one, and it's going to be a float. Works exactly the same way. Just give it a name, give it a default value of, let's say, 50, and then we can use this to even just drag and drop, actually, into whatever fields support that same type. So we can just drag and drop this into here, or very much the same way, we can just look for the name, and then it's in link inputs, user parameters, and then this name over here. Of course, in this case, I want this to be a multiplication, because I want these to be a little bit bigger. I'm going to set like 1.25, so that roughly 25% bigger, and then give in the size for them. And the wonderful thing about this is now both of these sizes are linked up to one singular parameter. And if I just save everything, go back into a level, and put this into the world, you see that, well, first and foremost, ends up way too big. It's good to check these things out in context sometimes. But with this, when you have a Niagara system asset in a Niagara actor, or as we're going to do in a moment, maybe a Niagara component, it has those user parameters exposed. If I make it do anything else, user parameters for this one does nothing. Only when I have this landing dust system chosen will it show the user parameters of that specific system. It just automatically populates that for you. If I now set this value to only being 10, you can see that the particle that spawns are much smaller. If I set it to 100, the particles that spawns are, well, a fair bit bigger. Now, these are just generally way more huge than I thought they would be. So let me just real quick go ahead and fix that, because it also just probably needs the shape location to be just much smaller. And then the initial velocity being 800, definitely also a bit much. Let's cut that in half. And then the drag just going back to 1 as well. Let's see. You want to make sure that you save all that stuff. And then let's see what that looks like in practice now. Still a bit much. And when I say a bit much, I mean pretty bad. Velocity back down to like 100 maybe. And then the default size, I think I set that to about 20. Probably could do with being even lower, like 10 maybe. You apply that, save everything to make sure that it's just updated, and that looks pretty decent. Now the spawn count definitely is too high, because we're spawning so many more particles close together that this probably could do with just being 50 instead. And maybe even just 30. 30 is a bit low. Let's go with 50. And when we change that, everything that has the default value, you will see, automatically gets updated to reflect that. It's a little too over the top, a little too obvious maybe. But again, this is the kind of thing that you can spend an eternity tweaking if you really wanted to. And a nice thing about setting these up as user parameters is that you can tweak them with real-time feedback in the context of your world, like this. Let's just go with a size of 10. So we'll set the default size for these to 10. Now, these user parameters can be set dynamically as you spawn in things as well. We'll probably look a little bit into that in the future. For now, I think it's a good idea to just get a move on and go back into our third-person character blueprint that we have somewhere in here. I think it's in tutorial player character. Because in here, let's see if we already have a on event landed or not. I don't think we do. So we can just, in our functions, look if we have on landed, add that into our event graph. And this is just an event that runs in response to whenever your character was falling and now is no longer falling. It has landed. It's really as easy as that. And we can spawn a Niagara system either attached to a component, which is nice for certain use cases. In this case, that's not what we're going to do. We just want to spawn it at a certain location. And the location that we want to spawn it at is just going to be at the feet of our character. And in this case, because we're using event landed, we already get a hit result. And we can break that hit result to get a whole bunch of different information out of it. One of which being the location of where the landing took place. Which is really nice, because wherever we landed is going to be where we spawn this particle system. So we just hook that into there. And then we add in the dust particles that we just created. We can set whether or not this should auto-destroy when it is done doing its loop. If it should auto-activate the moment we spawn it in. It's got some object pooling, which you don't need to worry about for now. And you can set its rotation and scale. Again, not going to really worry about that for now. And since this is a one-off effect, it's probably good for the system as a whole to just be set to, hey, you run once and then you're done. And we'll see that if I just jump and I land, it spawns them. Well, it doesn't spawn it at my feet, because what it does is it uses the location of my character. And my character's location is calculated from the middle of its collider. So instead, we probably want to use the impact point for where to spawn this thing. And that will actually spawn it at the feet, as you can see. So now, if we jump and we land, it's a bit obvious, it's a bit over the top, as I said before, but we can definitely see now we have a bit more feedback as to we have landed, just feels a little bit better, and we can do a whole lot of stuff. So next time, let's add in some more particle stuff, and we're going to dynamically make particles that are different colors, depending on some stuff. We've made this little particle system that happens when we land on the ground, and it's a bit much, maybe, but it always is this buffy white kind of look, and it doesn't look super good when we land on something that's green. And making this entirely dynamic is a bit bothersome, but we can do some stuff to using that exact same system that we have set up in the previous video. Still give it some different colors depending on some other code inputs. To take a look back at it, we have this dust system that we've created based on 2 different dust emitters. And this takes in, at the moment, just a size. But the emitters individually also take in a particle color. And much like we did with the size, we can just link both of these particle colors. We can make a new user parameter for that as well. So make a linear color. We'll call that dust color. And drag and drop that into our particle color here. Let's set the default value to something like a more green-blue, because we're going to need to kind of change this color, because this other one isn't pure white. I just made it a little bit bluish before, and then also a little bit darker. And for that, we can use the U-shift linear color input. And that's going to take a, well, linear color input. And I can just shift the U for this one. And now you can see I've got one color input. It's going to always be that color. And then the other system is that color offset a little bit. So let's offset it by about 10%. Just make it a little bit more dull as well, by setting the value, which is the brightness of it, to about 70% maybe. And then maybe this one is slightly more desaturated as well. And now if I make this pink, both of them will always be roughly the same color, just with a little bit of variation between them. That's fantastic. We're going to set the default color for it back to being a white type of color, because we can use that to really dial in the difference in value. Maybe even down to like 60%. Let's go with 50%. That seems pretty good. But we don't want to set this in a pre-set up way. We want to set this dynamically every time we spawn this thing in. And we're already spawning this thing in based on the player landing. When we land on anything, we use the hit result with the impact point to spawn the system there. That's what all of this has been doing so far. But now we want to set the color parameter that we just created, the dust color, based on some stuff. Relatively easy to do. We can just use the reference to the Niagara system that was just created when we spawned this in. And then we can set a color parameter, and that'll get you the set Niagara variable linear color node. That takes in the exact name of the variable. Because it's based on names, it's generally a good idea to just go over here, and you can copy the display name and just paste it in. That'll give you exactly the proper name, proper capitalization. Any typos that you make are going to mess this up otherwise. This will now just dynamically set whatever system we spawn in, the color for that specific system. We can promote this to a variable real quick, at least temporarily, so that I can show you if I now make this alpha, obviously 1. Doesn't really matter probably, but still. And I set this to being blue. I can jump, and the particles that spawn in will be blue. If I set this to being that pink color that we used before, it's a pretty good one, I can see that they spawn in being pink. So far, so good. Now all we need to do is write a little bit of code to decide what color this should be. And there's a whole bunch of things that you can do here. What I'm going to do is a fairly straightforward method of dealing with this. We already have a reference to the hit actor, the actor that we hit against. If we just get the component by class from that, and we just try to find a static mesh component in this thing, first and foremost, it's going to be important to check a is valid on this, because if this is not valid, we don't want to try to like set anything based on this. But if we did find a valid static mesh component, what we can do is we can get the material in any given index slot. A static mesh can have multiple materials on it. We're just going to worry about material 0, the first material that it has, and just use that to look up, hey, this material should use this type of color when we jump onto it. And the way that we do that is by setting up in our variables in the player character here. We'll just set up a material to color map. It's the first time that we're using a map, I am pretty sure. So we'll walk through that. We'll make this as a variable like any other. We're going to try to find a material, find material object reference, and then we change this from a single. We've already talked about arrays, I'm pretty sure. We're going to ignore sets. We're going to take a map. And a map is going to be a variable type that has, well, two different types. A key and then a value. And that's going to allow us to give in a key, so in this case, give in a material, and it's going to spit out the corresponding value to it. In this case, it's going to be a linear color. If we compile that, we can start giving in some values to this. And you can see that it wants us to put in a material here. If you find that you can't do it, it's probably because it's a material instance that you're trying to put in there, and we're just allowing normal materials in here. So you might want to give in a material interface instead. That allows you to put in pretty much any type of material. And then you will see that you should be able to drag and drop that in there. No problem. Good thing actually, because this get material gets you a material interface reference anyway. So it's probably what you want to do regardless. And then we just say, okay, this material, when we land on that specific thing, we want to give in, well, let's say just green. That makes sense in this situation, I would imagine. And we get that material to color map, and we can just use find in that. And we try to find whatever material we get from that component by class. And if this is something that it did find, it's going to give us a true out of the bottom bin here. So we also want to check that just to be sure. Because if it didn't find that, we're just going to go back to whatever the default color is, in this case, white. But if it did find something, we just give that in as the in value instead. And as easily as that, now it will spawn in green particles when we jump on this, and it will spawn in just the default particles when we spawn into literally anything else. And now everything in the game with this material will respond in this way. That does mean that if you have a bunch of different materials, you're going to need to set up this map to have a lot of entries, which is obviously not ideal. An alternative that is a little bit more broadly applicable would to instead be use a map with physics materials. But for now, we're going to keep it at just the way that it is. And I'm going to copy this thing over and just with the End key on the keyboard, snap it down to the ground and make a copy of this material. Call it MI, let's call it blue for material instance, well, blue. And then the surface option here, I'm going to just call this one blue instead. Give it to this object, just to show you how easy it is to now go in here and look up my material instance for blue and tell it, well, I want this to spawn in, again, alpha at 1 with a blue color. For some reason, my PC doesn't really like working with the color picker today. I don't know why. And without anything more than that, we can see this is green. Anything else is the default color, but this will spawn them in as blue. And no matter how you decide which color it's going to display, because there's a bunch of different ways that you could do this, you can set pretty much any type of this user parameter just with the corresponding setNiagara variable, and then in these parentheses, the type of variable. Now that we've played around a little bit with a handful of different particle things, I think it's a good challenge for you yourself to go in and make two different particle systems. A particle system that spawns in and looks like the player got hit, something that just tells the player alongside of the camera shake that we've introduced before that they got hit, and then a separate particle system that looks distinctly different in some way that spawns in when the enemy dies. And for bonus points, if you have multiple different enemies, maybe make them use different colors or otherwise different properties with the same system, depending on the different type of enemy. I have 2 different enemies over here, and if this one dies, maybe those are brown and green particles, and when this one dies, presumably they would be orange colored particles instead. And maybe they have a different velocity, or maybe these ones go upward a little bit more, and these ones go out a little bit more. Try to experiment around a little bit with a bunch of different particle settings by making a Niagara system that's potentially built out of one or multiple emitters that are easily reusable by just changing around a couple of parameters. It's good to get into the practice of not just making, oh, I'll make this into a whole new system real quick. Because you're going to end up with hundreds of systems. Despite the fact that we're doing more art-related stuff now, the same principles that we discussed previously in programming still apply. Setting up reusable stuff is always a good idea. You don't want to script out the exact same bit of code 10 different times. You make that into an event, you make that into a function, and then you just call that event or function. Same thing here. You don't want to set up the exact same behavior for particles with just a slight difference 10 different times. You make an emitter and then just tweak that emitter. Or same thing with the systems as a whole. To round out our focus on particles for this first section of adding juice to our game, we've made this particle system that spawns in when I land on the ground. And we've even made it different colors depending on exactly where we land. But it's still using the default sprite renderer material, and honestly, that's fine. I just want to take a look at some particle-based materials today a little bit, both so that we can make this particle effect look a little bit more interesting than it does right now, maybe, and also as an introduction to materials in general, because we haven't really talked about those all that much. So let's go ahead and make ourselves a particle material. I'll add in a new folder here for materials if we don't already have one. I don't think we do. So add in a new folder for materials. And I'm going to just make a right-click new material. Call that m underscore for material underscore. And I don't know, we'll call this dust particles. Let's open that up. With materials, there's a handful of different material domains that we can work off of. Surface, which is usually for things like 3D models. Textures for characters, props, assets, whatever. A decal, which we might look into in the future, not important right now, but those are just projected images that you can put onto surfaces. Light functions, which are materials that you can put on lights to cast lights in certain patterns or whatever. Volumes, not going to worry about that too much right now. Post-processing, same thing, don't worry too much about it for right now. A user interface, which is for, well, any UI elements. We're going to stick with surface here. And then we have a whole bunch of blend modes. Generally speaking, you want to stick with opaque or masked as much as possible, because anything that has any real alpha is going to cause major performance impacts, because if you have multiple materials that all have a see-through element to them, overlapping on the same pixel, that pixel becomes very, very expensive to render suddenly. Whereas an opaque material is just always going to be one object occupying that specific pixel on your screen. A mask material is a material where pixels of the object can either be opaque or entirely transparent, but nothing in between. So there you still don't have multiple objects occupying the same pixel, because if you have, well, a part of it masked out, it's just 0% visible. So it doesn't come with that same performance impact. Additive is usually what you use for particle effects. Not always. You might have a reason that a particle effect needs to be translucent or opaque or whatever, but usually particles end up being additive, where it is kind of similar to being translucent, but instead of, if we have the camera here for our game, right, and we have surface number 1, which is at 0.5 opacity, and we have surface number 2, which is at 0.7 opacity. This becomes really difficult to render if we have just an opaque, like 1.0 opacity behind it, because what colors are these pixels going to be? They are the color of this surface, plus 70% the colors of this surface, plus 50% the colors of this surface, and that's why that becomes really, really difficult to calculate and render on a large scale. However, additive doesn't really have that same issue, because all it does is it just takes this color, and then adds this color, and then adds this color. So if this is red, and this is pink, and this is yellow, it's just going to take the RGB values, R, G, and B, of all those together. Well, red would be 1, 0, 0. What did I say here? Pink would probably be like 1, 0.8, and 0.8 or whatever. I didn't leave myself a lot of room down here. And I think I said yellow here, which is red and green together, and then no blue. This is relatively much simpler to calculate for every individual pixel than the translucency would be. You also note that if we just make this a little bit clearer to see, these values very quickly go over a value of 1. So they end up just kind of clipping over white. And that's also why generally you don't end up using the base color for this. You end up using the emissive, because emissive works very well additively. It just starts having this little glow around it instead. If you want to have a reference for a particle material, you can just open up the default particle material, and you can see that this is set to surface, additive, and unlit as well. So that's the last thing here. The shading model is default lit. That just takes in all the lighting information and decides how that surface should look based on lighting information. But we have a bunch of different other things as well, one of which is unlit. This ignores all other lighting information in the entire game, because you're just going to immediately give in an emissive color into it instead. If you don't have lumen enabled for global illumination, this emissive color is more or less just explicitly stating what color the pixels of your shader are going to be. If you do have lumen enabled, there is a thing where emissive materials actually emit light into the world as well, which may or may not be what you want, so be aware of that. But for particles, surface, additive, unlit is generally the way to go. Then we can look at all of what is happening here. We have a two-sided sign, don't really care about that for the time being. It uses a particle color, which is a node that we can use for materials that are effective on particles. It just takes in whatever the attribute for that particle's color is. So in this case, the particle color is being set with this like dust color. That will just be provided in for the material to be able to use. So let's just copy that particle color. And that can go straight into the emissive here. And now we can see that it shows us this nice little round preview. However, that's not entirely accurate, because these particles are going to be appearing on 2D planes, because they are sprites. So instead of previewing this on a mesh sphere, we're going to be previewing this on a plane, and we can see that we just have a white square. And that will be correct, because if I now go into this, let's go into the emitter itself, actually, and I change out the material that we're using for this one that I'm making right now, you'll see that everything just becomes a white square. Simply as that. And at the start here, you can kind of see how that additive stuff works. Because there's so many of them occupying the same pixels, it kind of becomes a little glowy. Because it does white plus white plus white plus white, which just becomes, well, very bright. And it just sees that as something that has this like halo glow effect around it. Let's make these go back to being round, first and foremost, instead of being squares. And we can look at the default sprite material. And this uses a sphere mask. I don't personally much love that. What I like to use instead is use a gradient radial exponential. And if we just put this directly into the emissive color, we'll see that this is what that gives us. It just gives us a 1 to 0 fall off from center to edge. We can give in a whole bunch of other different inputs, the UVs to make it tile, grow, shrink, how big the radius is, how dense the fall off is. We can do a whole bunch of interesting stuff with this. However, for now, all that we're going to do is we're going to take our particle color and multiply it with this gradient exponential. And then we'll see that we have everything back to being round. However, it might not be very obvious, the alpha isn't doing anything at the moment. Our color as a whole is just kind of going down in brightness, which in an additive material does the same thing as the alpha going down, because you will notice that the transparency, which exists somewhere in here, or opacity. So let's just put the opacity override for now into there. And that doesn't visually probably make too much of a difference, but now it's actually using the alpha again. So we've recreated all this with a lot fewer nodes, admittedly. Now, how do we go from here? What I want to do is I want to add in a bit more detail, because right now it's just this blurry, puffy smoke, and I want to add in a little bit of noise into that. And the way that I'm going to do that is by adding in a texture sample node. And this lets us, well, sample a texture. Give it a texture and it will display it. Unreal, as long as you have starter content enabled, I think, will come with a handful of different noise patterns. And you can always import your own textures as well, of course. But we are going to use some noise that I like the look of. If you look for Perlin, you also have this Perlin mask texture, which is just a little bit higher resolution. And the way that you scale that up is by adding in a texture coordinate node. So if you just type in text coord, get texture coordinates, and that just gives you the UV coordinates. I'm not going to go into a super deep dive on all the material and frankly even maybe all the particle stuff, because I have a dedicated playlist to explaining pretty much everything you need to know to get started with materials. And I don't want to repeat all that information in here. We're just going to go through the very basics to get you started, to get you working. But if you want to understand more about, okay, but what does this actually do? How does it actually work? What do these numbers mean? That playlist walks you through it a little bit more. But for now, the texture coordinates are just your UV space, and your UV is U and V. So all that this is saying is, okay, there is one U and one V existing for our texture. So that's just going to display our texture the normal way. If we put this into the UVs, displays it the normal way. If I say the UV tiling, I wanted to tile 4 times in the U, it's now saying, okay, there is 4 U's, so this texture should be displayed 4 times in the left to right direction on whatever surface we're trying to show this at. If I then also set the tiling for the V to 4, it now also is displaying it 4 times in the bottom to top direction. If we set this to 0.5 instead, that starts allowing us to zoom it in a little bit. So let's put our particle color back into the emissive color here. And we're going to use this radiant exponential along with our alpha. We're not going to actually use this alpha opacity override anymore. We're going to use this alpha to drive how far we're using this gradient exponential at. First thing to do is just to subtract our alpha from it. That's the easiest thing to do. And if we do that, and we put that into the emissive or the multiply here instead, when our alpha is 1, it just makes everything disappear. This works the opposite direction of how we want it to work, right? Because now when our alpha is 1, our particle is gone, and when our alpha is 0, our particle will reappear. Matter of fact, I can show you that. This is a stand-in for alpha being 1. This will be a stand-in for alpha being 0. And at 0.5, it will be a little bit of a smaller circle that is also dimmer. We need to invert our alpha. And for that, we do 1 minus x, and that is exactly what it sounds like. What this does is it pretty much just introduces a subtraction node, which is just 1 minus whatever we put into it. And as long as the values that we're working with are on a 0 to 1 scale, pretty much what that means is just invert. So 1 minus x, and put that into there. And now we have our alpha working the way we would expect it to again. You will see that if we go back into this now, and we use our actual sprite renderer in here, that even if we don't have our scale sprite size set up, we still have these sprites now shrinking down. Not because the sprite is actually shrinking down, it's because the material itself is using the alpha to shrink down what part of our sprite is visible. If we then just combine that with this texture sample, we can make an effect where we kind of fade through using this noise texture. And the way to do that is just with a node called a height lerp. The height lerp is going to be interpolating between two different inputs that are going to be colors. And then we have a transition phase, which is how far it is going to be between 0 and 1, and the height texture, which is the, well, texture as to how it's going to interpolate through that. We can just put our noise texture into the height here. And if I then add in a scalar, just holding down 1 and clicking anywhere in the graph gives you this little scalar nodes, which just is a float. Set that to 1 and go into the transition phase. Now everything is entirely black because it's just 100% displaying B. If I set this to 0, it's 100% displaying A. But if I set this to 0.5, you can see that it is now interpolating through that and showing some of this noise pattern. It might become a little bit more obvious if we don't do this with just 0 and 1, just black and white, but just straight up add in two different colors. So let's just make this blue and go to like color like magenta pink type of deal. And if I'm at 1, it's entirely pink. At 0, it's entirely blue. 0.2, it starts kind of blending between these based on this texture, which is fantastic because that is what we want to do. Is instead of just doing this as a multiplication, we're going to be doing this as a height lerp. So an alpha of 0, there we choose 1. That's just going to be entirely black. It's just 0. At an alpha of 1, we want it to be pretty much entirely the particle color, still multiplied by the gradient radiant exponential, because we still want it to be that circle formation, right? There again, simulating alpha 1 being this, alpha 0 being this, alpha 0.5. Now we can start kind of seeing a little bit of noisiness getting introduced in the way that it fades away. And we can just put the actual alpha into the transition phase. Don't need to do any of this subtraction stuff anymore, because that's what this height lerp is now handling entirely for us. We can add in a little bit of extra contrast if we want the... I'm gonna just add in that scalar again real quick. If we want this to be just a little bit sharper, a little bit more, well, contrast rich, we can add in some more contrast. By default, the value is 0. If I just set this to 1, you can see that the contrast of the height map is just a little bit higher, which then in turn makes it a little bit more visible with how we introduce that detail. So that's probably a pretty good value to use, like 1, 1.5, maybe 2. And now with all that out of the way, if we go back into my emitter, you can see that now it is kind of more fading away, but you can see everything is using the exact same texture at the exact same size, and it feels very much like your particles are kind of like just tiling the same tile, because, well, they are. And there's a pretty easy fix for that, because if we take these UV coordinates and we just add something to them, we can create a random offset per particle, because we have this particle random node. And this is just a 0 to 1 value, random, that is unique per particle that spawns in. So if we multiply this with a value of just any value, it's good to use two different primes here, ideally. But 0.13, and then also multiply it with 0. What's another good number that's not going to overlap too much with 13? I don't know, 41. Is 41 a prime number? I don't know. As long as these two are very dissimilar and don't share too many like dividers, which is why ideally you want this to be primes, that just prevents patterns from popping up. We'll append these two together as a vector, and that's just going to put them together into a XY combined value. The same way that this textual coordinates is an XY combined value. They're called U and V when you're talking about texture space, but XY, UV, AB, they're just names, they're just labels. What matters is that we have two numbers combined into one package. And when we have that in both of these situations, the UV and this random offsets XY, we can add them together And now every single particle is going to have some amount of random offsets, and that's going to make them look a lot less tiled, as you can see right there. And that just makes it look so much more interesting immediately. And you can see that we're starting to introduce a whole bunch of detail here, while keeping the particle count itself down relatively low. Because we don't need to spawn in 100,000 particles to get all of these wispy details, because the shader itself is taking care of that for us. Now, there's a lot more that we could be doing, taking in the particle size as well to scale up or down the texture as the particle itself grows. We're not going to worry too much about that for now, but we're height looping through this to just make it fade out in a more pleasing manner. And if we apply that and we go into the proper actual system, we'll see that one of these doesn't seem to be using that material. This one is, this one isn't. So copy this over and make this one also use it. And now both of our emitters are using that value. And as a result of that, we can just see that it does that in the world now. That makes our little thing look a little bit more like fire than dust, admittedly. Maybe it shouldn't look as much like flames as it does. But hey, if you're making a kind of like fiery type of deal, this would have worked out pretty well. In this case, it's probably a little too high in detail, too high in resolution. So we can just kind of play around with it, what it looks like if we maybe set the tiling here to 0.1 instead. That's going to make everything zoomed in so much more, which means that there's going to be less fine detail in the whole thing. And that might still make things look a little more interesting in the way that they fade away. But now it feels a little bit more like dust, maybe, than flames, potentially. And if we want to test that out in our material preview, it is relatively easy to just plug in a value of 0.5 or something like that and just see what this looks like. Because maybe we even want to go a little bit more down, like 0.05 or something like that. Really make sure that it is a very, very low detail kind of transition that it creates as a result of this. And that is a fair bit better already. It probably also wouldn't hurt to just keep tweaking this forever and ever and ever, as always. But now I feel like maybe these particles also just exist for a little longer than maybe they should. So we can kind of make that go a little faster as well. And that then has influence on probably the physics of them as well. And you've seen me go over a lot of tweaking of stuff in the past, so I'm not going to bother you too much with me tweaking a whole bunch of numbers here. But we have a particle material now that just made our particles look ever so slightly more interesting without adding in a whole bunch of extra particles for that detail. I want to talk about post-processing, which is just taking the image that the game engine will render with all of the lighting, all of the models, all of the everything that we've made, and making some minor or sometimes pretty major adjustments to it to really create the look that we want, either globally or in a localized area. A very common way that you see post-processing being done is with a post-processing volume. If we put that anywhere into the world, as long as our camera, not our player, but our camera, is inside of this little box here, this volume, it's going to apply the post-processing effects that we set up inside of it. And post-processing can mean a whole bunch of different things. Let's make the volume a little bit bigger so that we can more easily walk in and out of it a little bit more obviously. And we're going to put it around this ramp over here. In our post-processing settings, we have lens properties, color grading properties, film properties, whether or not it uses global illumination. So you can very much enable and disable global illumination, that being lumen or whatever other methods might exist in the future, on a per area basis. Some areas you might not want to be globally illuminated and you want to just use traditional light baking. And then some areas you might want to throw all that traditional light baking out and rely on global illumination. Reflection settings, all this type of stuff. Post-processing materials, which are materials that you can make specifically to get a certain effect applied to your image as post-processing. This is usually where you do things like cell shaders or pixelation shaders or whatever type of effects you want. You can effectively program anything in there. We've got some ambient cube maps, which is more or less just ambient lighting without actually having to place the lights. Ambient occlusion, motion blur settings for specific areas, also really, really cool. Some film grain settings, path tracing, which we don't really care about at all. Long story short, there is a lot of things to take a look at, and we're not going to be able to look at all of them in a lot of detail. So what we're going to do is we're going to mostly limit ourselves to the color grading here. And if we look at that, we have a couple different submenus. The temperature is how warm or cold the image feels. Cold being more blue, warm being more orange. There's a couple of different things that we can use to drive that, whether we use white balance or a color temperature. And these are just numbers that you kind of need to get used to. There is a lot of information online about what sources of light emit what temperature of light. Something like the sun would be something in the area of about 6,500, but could go down to as low as 3,000 or 4,000 at a sunset, where the sunset obviously has very warm, very orange light. But it also could go up as high as 7,500 on a overcast, cloudy day, which also makes the light a little bit more blue. If we just play around with this is what the difference is between white balance and color temperature. If you have it set to white balance, a higher number makes it compensate. So usually a higher color temperature number is a colder color temperature. It's more blue. When you set this to white balance, it's going to add in more orange to compensate for that. And when you do it lower, it's going to add in more blue to compensate for the fact that the lighting itself will be more orange. Personally, I don't think using this makes a lot of sense, because if you're going to look online, you're going to find the actual Kelvin, as it's called, degrees Kelvin, for what different light sources emit, and that is what the actual color temperature is. The lower the value, the more orange we get, and the higher the value, the more blue we get. So we can make the image just a little bit more blue, which, generally speaking, 100% on point color balance looks a little bit boring. If you want something to feel a little bit more homely, a little bit more cozy, you make it a bit more orange. If you want something to feel a little bit more fresh and like crisp and sparky and that kind of stuff, you add in a tinge of blue. We might have talked about this before in a previous video, but the same way that if you're doing any graphical work, if you want something to be 100% white, don't make it 100% white. What you generally do is you make it very, very light blue. Because believe it or not, something that is very, very light blue is experienced as being more white than pure white. If I go out of this, you'll see this is the actual look that we have. Obviously, we do have it being a sunset, so the whole scene is a little bit more warm. This kind of just corrects that back to the normal look of it. But the shadows now become a lot more blue than they would be if this was just a noon time setting. We will also notice, though, that there is a little bit of a magenta hue to this entire thing. And that is because color balance has two separate, almost axes. Warmth, which is orange to blue, and then we have the tint, which is magenta to green. If we try to adjust the tint, we can see we can add in a bit more magenta, and well, we can add in a lot of magenta if we want to, and the entire thing becomes pink shifted. If we add in the other direction, we can see we start adding in more and more and more green until the whole image has a green look. Generally, as you add in more blue, which we've done here, you're also going to want to add in a tiny bit of extra green to it to balance out and really get things looking properly, accurately, with a good white point. That is just color correction. What we use post-processing for is something called color grading. And the difference there is color correction is just taking an image and making it real life accurate in terms of colors. Color grading is using the same tools to make an image look and feel a certain way. So we want this to be maybe even a little bit more blue, and then add in the magenta just for the sake of the effects right now. These temperatures are probably one of the more important things to take a bit of time to look at. Everything else should be fairly straightforward. Then we have all of our color wheels: globals, shadows, midtones, and highlights. An image is generally, in color grading, split up into 3 sections. The shadows, which are the darkest bits of the image, so you'd be looking at areas like over here. The highlights, which are the brightest bits of the image, so those would maybe be the clouds in this case. And then everything in between is the midtones. Where that cutoff is between shadow to midtone and midtone to highlight is usually adjustable. So you can say that the bottom 25% of brightnesses count as being the shadows, the top 25% count as highlights, and the middle 50% counts as midtones. Or maybe only the bottom 10% is shadows and only the top 5% is highlights. And obviously we have global, which just ignores all that and applies color changes to the image as a whole. If we take a look at the shadows here, and I'm going to pull back my color grade here for the color temperature a little bit more, because I want a somewhat more neutral look as we go into this. We can set up the saturation, the contrast, the gamma, which is more or less a brightness offset, gain, which is also a brightness offset. These two work in slightly different ways. On a technical level, I believe gain just boosts all the brightness up equally, while gamma just squeezes down the curve in brightness. So if we have a brightness that goes like this, and this is the shadows, for instance, right? What gain would do is it would just take this entire section and move it up like this. What gamma would do is it would proportionally edit this to maybe make it go a little bit more like this. So the gamma would take out some of the contrast as well, but it wouldn't create this weird little cutoff. That's a very short and very over-rushed explanation of it. In general, both of these make it brighter, just in slightly different ways. And then we have the value here that says what is the maximum amount of brightness from a 0 to 1 value. In this case, that's about 9% brightness, where it still considers things to be shadows. Let's take a look at just changing the saturation and the contrast a little bit. If we open up any of these submenus, they come with even more submenus. We can individually change the red, green, or blue channel, or the luminance. So we can change the color balance of the shadows, or how bright the shadows are as a whole. If we just, well, this is the saturation, so that's not going to do that much in this case. Let's do this with the gamma instead, as an example. If I pull up the luminance of the shadows, you can see that the shadows just kind of brighten up and almost disappear. And at this point, the shadows are brighter than the midtones, which is not generally what you want to do. But maybe you want to give a little bit of a boost to the shadows so that the darkest parts of your image aren't quite as dark. And oftentimes what you end up doing with shadows is making the shadows a little bit more cold, so a little bit more blue. So we just take the gamma for the blue specifically now, and we pull that up. And you can see that just makes all the shadows go a little bit more blue without making them necessarily all that more bright. We can also set the contrast, and instead of using these sliders, we also, by the way, have HSV. This is RGB, so we can individually influence the red, the blue, and the green channel. HSV is hue, saturation, and value. So this is, well, what color it is, this is how saturated that color is, and this is how bright the color is. We might take a look at that for the global changes that we're going to make in a moment here. If you don't want to bother with all this, all of these also just have a simple slider that just increases or decreases the corresponding value here. So I can just increase everything to do with contrast in the shadows by about 40%. And now the shadows just have a bit more contrast. They're a little bit more blue, and it just, well, it has a certain look to it. That's the shadows. Now, the midtones, the highlights, they do the exact same thing. I'm just going to go into the midtones and saturation. It's going to go up. So everything that is above that 9% brightness that we had set up here in the shadows. Now, if we open up the highlights, I'm assuming that this is going to be like 95 or something like that. Yeah, the highlights go from 50% to 100%. So that's the top 50% of brightness in your image. Everything between that 9% and that 50% brightness is considered to be the midtones. So that's what's getting affected here. You will see that all this stuff that is considered shadows, even if I pull this all the way up, it doesn't get affected at all. If I put it all the way down so that there's no saturation in the midtones at all, midtones and gray. The shadows, however, still have color in them, because this doesn't affect anything that is either very bright or very dim in its brightness. Maybe a little bit more saturation in the midtones also creates a bit more contrast here. We could go back in here and say that we want the saturation in the shadows specifically to be a little bit less. And then finally we have the highlights, where at this point I don't really know what I would do to show you this, but maybe we just, well, let's do the gain. Do we even have anything that is considered a highlight in here? Only this area over here. So I can do whatever I want here, and it's not going to have a visible difference at all. Only the sun itself there has a little area that is affected by the highlights. So if I pull this all the way down, we can see this is everything that is considered a highlight. However, if I pull down the highlights minimum, you can see that that starts affecting more and more stuff in the sky. We go all the way back up here to global. We have the exact same tools, but this will just work on every pixel on your screen. So if I pull this all the way up, doesn't matter if something is dark or bright or anywhere in between, it's just going to affect the whole image. A lot of your color grading is going to come from here, because this sets up the general look of your scene, how saturated it is, how bright it is, and then tweaking the individual shadows, midtones, and highlights just is a good way to create contrast between those different areas, be it in brightness or be it in color or whatever you want to do with it. And we've been in this post-processing volume for a while now, and this might start looking pretty much like just, okay, this is normal now, right? But if I move back out of it, you will see that no, there is a pretty big difference between the way that these images look at this point. And that's the most important one for the time being. There's a whole bunch of other stuff that we can do here as well. We might want to take a little look at the lens, because we can add things like bloom, a dirt mask, which just adds a little bit of dirt as an overlay. Chromatic aberration is a fun little effect. It separates the red, the green, and the blue channels, so that we create a bit of like, well, this effect that you see right here. It's kind of like, and it generally does that less in the center of the screen, as you can see. At the exact center, it doesn't happen at all. And the further we go out toward the edges of the screen, the effect becomes stronger. We can set that start offset to be a little higher, so that it's only at the very edges of the screen. And of course, we have the depth of field, a very, very famous looking effect. If we just enable a couple of these different things, we have a whole bunch of actual camera technical specifications here. The bigger your sensor width, generally, the more your depth of field is going to be obvious and the more you're going to be seeing it. You don't see anything happen initially at all. And that's because we don't have a focus distance set. So we can set a focal distance, and you can see that that starts bringing things in or out of focus. And now, if I decrease or increase the sensor width, you can see that it has an effect on how blurry things become. Pretty much everything else here is just to slightly change the characteristic of the way that the blur looks. I encourage you to just go through this one menu at a time, play around with the sliders and see what ends up visually happening, because there's just so much here to talk about that I don't think I'm going to spend hours on hours just going through every single individual option here. One last thing that I do want to mention though, because it's going to play into the effects that we're going to be making here in this video, because we are working towards something here, is in the image effects. We can add a vignette, and that just makes the corners of your image more dark. That is the post-processing volume, and you can see it kind of interpolates a little bit as we go into it, so it's not a hard cut in. It's a little bit of a fall off that interpolates into the effect. And if we look for the blend radius, that is the thing that decides how softly this interpolates. Right now it's at 200, which means that it takes 100 units of interpolation between being entirely off and being entirely on. But we can set this to, let's say, 1000. And now even outside of it, the effect of it is much more obvious, and the interpolation is a lot more gradual in and out, which is just a little bit more nice for the player to walk into. You also can set these to being unbound, which gives them an infinite extent. And now, no matter where in the world I am, this thing is going to apply its post-processing. It's no longer just within the area. However, if you want to do that, you can, instead of doing a post-processing volume, you can set these exact same things up on the player's camera directly. The downside to that is that if we go into the player character's blueprint and we go into the camera, we have all of these same post-processing effects here. We have the color grading, we have the lens, we have everything that we could ever want. We just don't get a live preview of what we're doing and what it looks like. It's a little annoying to set up that way. What we can do is we can just pull one of our players into the world, and as long as we have it selected, we get this little view of what its camera is going to see. And if we just scroll down and select that camera component, we very much can find its post-processing and start just doing our adjustments here. For instance, let's go into the gamma, and I'm going to set this to HSV, which uses the hue, saturation, and value instead of RGB. I'm going to just saturate this up a lot more so that it becomes a lot more red. You also can use this little wheel over here to set a color tint. Might be good to pick a kind of rough look that you want and then just dial it in a little bit with the sliders themselves. And then I also want to go in and in the lens image effects, I'm going to add in a very strong vignette as well. And this is going to be what our game looks like when we are very, very damaged. And now that we have done all that, we can set this instance of our blueprint to be what our blueprint's defaults will look like. And we can do that by just going in here with it selected and added this blueprint actor. It falls down a menu, apply instance changes to blueprint. And now everything that we have set up will be the default for our blueprint. So if we just drag in a new one, we can see it immediately has that effect. If we start playing the game, it spawns in that blueprint with those effects. But now our entire game looks red and vignetted up, and that's just maybe not what we wanted to do. And that is where we do the very, very last important thing. In the camera options, we have a post-process weight blending, which can blend between the post-processing effect being active or not being active. By default, obviously, we want that to be set to 0. I usually just type in blend to find it. I'm going to set it to 0. And it's going to just increase this blending depending on how much HP we have. Remember in the past when I made this little function here, set current player HP, and I said, well, if we ever want to add in any amount of new code that always needs to run in response to our player's HP changing, we have it in one centralized place. Now is that time. Open up this function that we have here. It wasn't doing that much before, but now we pull in a reference to our camera and we set the blending for our post-processing weight. And we can't just set it to our new current HP because obviously there's going to be a value probably in the tens or in the hundreds. We want this to be a 0 to 1 value, and we want it to be a value that reaches 1 when our HP is 0, and it reaches 0 when our HP is max. So how do we do that? Well, first and foremost, we take our struct out for our BP member stats. We break it so that we get our minimum value, maximum value, and our current value. We need to get the percentage of our HP in this case. So we take our current value and we divide it by our maximum. That way we get a percentage on a 0 to 1 scale. Still though, if we put this into here, this is going to work the wrong way around. Because this now is just the percentage of HP that we have. And we want this to kind of be inverted. So all that we need to do is subtract 1 minus that amount. If our percentage is at 100%, 1 minus 1 is 0. This thing is using no blending at all. If our HP is at 30%, this will be 1 minus 0.3, so we'll be at 70% blending. If our HP is at 0, 1 minus 0, it's fully blended in. At which point we will also be dying, so it doesn't really matter that much at exactly 0. However, we have a couple of different functions here for setting our HP. We have subtract HP, increase HP. All that is not exactly ideal, because we want this to happen in response to all of those. So instead of just doing this set member stats that we have done in the past, what we're going to do is we're going to replace this with our set current HP function, because we're already just setting the current value here anyway. And then we can remove this set member and this call on new HP, because that's also already done within this function. And with that both increasing and decreasing our HP, we'll also now use all the code in our setting HP directly. Something that we probably should have done to begin with a long time ago. And now you can see why, because I want to add a little bit of code, and instead of adding it in 3 places, I added it in one place where it is logical, and then use that one function in everything else. So we set current HP, put in our new current HP, and we delete both of these, which simplifies things down a little bit as well. And now we'll be able to see if I get hit, we'll become a little bit more red, and if I get hit more, we'll become a little bit more red, and so on and so forth. The vignette will be increasing, and if I manage to increase my HP again, which I don't know if I have a hotkey still set up for that, I get damaged. I just get damaged a couple of times here. I press H to heal myself, and I'm back to full HP, which also means, as you can see, post-processing has been reverted as well. This post-processing volume exists over here, so as I walk into it, we will see the post-processing effect that we set up at the start of the video, which looks a little weird and a little bad. That in a nutshell, well, a very, very big nutshell, is post-processing. We've talked about it in volumes, in the player camera, how we can blend it in and out dynamically based on some gameplay efforts. And it really helps just making the game feel more unique, give it a visual identity, but also doing things like adjusting that post-processing based on some gameplay inputs to make it an interesting part of this adding juice and adding interactivity, adding feedback toward the player. We may have done a lot of work already in juicing up our game a little bit. We've got this post-processing stuff happening, camera shakes happening, more camera shakes happening, all that type of stuff, particle effects that even kind of are dynamic as to what color they are depending on where they spawn in. A lot of stuff, and still it feels a little bit lifeless. Part of that is because we're not going in through and doing a lot of polishing passes over all of this, of course. The models are very low poly, kind of poorly animated, and everything we're looking at here is kind of surface level. Hopefully, if you're following along, you're taking some breaks and playing around with things, and what you have actually looks better than what we're looking at here. But a huge part of what we are missing is sound. The entire game still is 100% silent. Today, let's just add in the first couple of sound effects to get you used to the workflow of working with sound. There is a lot of stuff that we could be doing here with dynamically pitching it up and spatial sound, different volume related magic. We're going to keep it relatively simple. We're going to just add in a handful of sound effects with a tiny bit of randomization. And that's instantly going to make us feel a lot more at home in this world. A very nice website for this type of stuff, if you don't have a huge sound library or any subscriptions for anything, is freesound.org. Do make sure that you take a look at the licensing agreements for it all. I believe you need to credit the sound creators if you use any of these sound effects in anything you make. But if we just look up footsteps, this one right here is pretty decent. It's just a single footstep, and often it's nice to have a bit of variation, have a couple of different footsteps to work with. This one sounds a bit better. I like this one. It's not ideal, but it'll probably do just fine. And then we'll import it into Unreal. I'll make a sound effects folder, and I will just make a new folder here with, called something like source. These are going to be all the source files, and drag and drop that in. This is going to import as a file media source. Not ideal. We want to import this as a wave source instead. If we open this up, it's essentially the same thing as if we imported it as a video texture. Not great at all. You can try to find some online converter or whatever for whatever file type you got, either being MP3, in this case it is a M4A file. Instead, what I'm going to do is I'm going to open up Shutter Encoder, which is a free just transcoding tool. Can take in almost any codec, any file format of video or audio that you want, and output it in anything else. So just drag it in here. We choose a function. We're going to translate it into a WAV file, and we just start function. Let's get rid of the media source version of it, and then we can import the WAV file instead. And this is going to import as a sound wave asset instead of a media asset, because it recognizes, hey, a WAV file is sound. But even if we do that and we open this up, it is just a whole bunch of information, and we want these to be individual footsteps. It's just one file with a whole bunch of footsteps now. So we'll need to cut this up into individual files with individual footsteps. Unreal does have a built-in plugin for a wave editor, I believe. I instead open up Audacity, which again, entirely free, drag it in here instead. And what we're going to do is I'm just going to individually export these as footsteps, which I do by just making a selection, going to export audio. I want to export it to my computer, give it some name like footstep 1, and I want to export only the current selection in this case. Then I browse to wherever I want this thing to be saved at, and we do the same thing again. And just like that, we've got 10 different files with 10 different footstep sounds that I can now all just select in my Explorer and drag in 10 different footstep files. From here, there's a couple of different things that we can do with these. We can just play one of these and be done with it, or we can put all of these into a different file that's going to randomly pick one of these each time. If we just look through for sound, we have a good few different things that we can do. I'm going to use a sound cue. You could alternatively start using Metasound, which is Unreal's much more built out sound solution that lets you dynamically change how sound is played back. Sound cues are just the older, much more bare bones version of that, but also are a little simpler, and while they don't offer all the dynamic fun stuff that Metasound can, it's good enough for what we do right here, right now. So I'm going to make a sound cue, and we'll call that SQ, sound cue. It's not technically spelled with the Q, but it gets the point across. And we'll call that footsteps. If we open that up, we'll see our sound cue. And in there, we can just drag in all our individual footsteps, and it's going to drag them all in. And what this does is it gives us the capability of creating essentially a blueprint graph for how sound plays and what sound plays. So if I just give footstep 1 into the output and I play it, it's going to play footstep 1. If I just select all of these and I say I want to pick a random one out of them, it's very nice connecting all of them up for me. And now what it'll do is it'll always pick a random footstep. And just like that, we already have every step that we're going to take, 1 to 10 sounds playing just randomly. And that could be enough. But to add a little bit of extra, we're going to add a modulator into this. And this just adds a little bit of randomness into the pitch and the volume of each step. Either 5% up or 5% down, or anything in between. And that makes these 10 different footsteps suddenly become essentially infinite variation. Because a footstep 1 here, pitched down 5% or pitched up 5%, is going to sound significantly different enough to your ear that if you're not paying attention, you're not going to tell that it's the same footstep, especially if it gets mixed in with 9 other footstep sounds randomly. So we can just play the cue. And that is what our footsteps will sound like. Now we just need to play them every time our character steps on the ground, which is a lot, but luckily also not that complicated. I'm going to delete this character, by the way. I don't know why that exists in the world. If I go into the player here, we can choose in its assets, in the animations that we made for it, in the animation sequences, we have our walk cycle here. We also have a run cycle. We're going to need to go into that in a moment as well. But we have moments where he steps his foot down. In this moment, I want to play a sound effect, and we can do that very, very easily, which is right-clicking, adding a notify, and Unreal comes with a play sound notify. And all we need to do there is just play our footsteps sound cue. We can even multiply the pitch or volume within this notify. So if we have a notify where we want it to be a little bit more loud, like when we're running, we probably want it to be a bit more loud. When we're walking, a little bit more quiet. So let's say that this is a volume of only 0.7. And then the next footstep doesn't actually touch the ground, I notice now. But we play it again. And then maybe this should be at the end and not at the beginning. Let's see. It even plays it in the preview for us. So we can see we have sound playing now. Fantastic. If we copy this over real quick and we go into our run cycle instead, we have a very bad animation, by the way. Maybe set this up to be about 1.2, a little louder. And then at the very end again, when he lands down, we also want to play it as well. It's a very fast animation. I think in reality, we do play it back a little more slowly. But just like that, we don't need to add any other code in our blueprint or our animation blueprint or anything like that. We already have our character making sound. There's one issue though, because the enemy uses the same animations as us. It plays the sound also when he walks. And this play sound is a little annoying because it more or less just plays it wherever it happens in the world. Even if I'm very far away, it's going to be playing it, and we don't really want that. And that is where we get into sound attenuation. Open up this again over here, and we select the output. We can set a attenuation settings assets. We can also just override it where we can set everything manually. But if we set the attenuation settings instead, we can make this into an asset, which is easily reusable. And we'll call this base sound, something like that. If we open that up, we can see how the sound gets attenuated. In other words, what the fall of forward is going to be, how it's going to work spatially. If you have a stereo setup, having it play more in the left channel or more in the right channel based on where the character is in relation to the camera. We don't really care too much about the spatialization for now. All that I want is it to attenuate for the volume. So we have that enabled. We can set a couple of different fall of types: linear, logarithmic, inverse, natural sound. We can give in a custom curve. I'm just going to keep it at linear for now. The attenuation sphere, we can set that to being, well, a sphere or a capsule shape, a box or a cone around the player. Usually a sphere makes the most sense. The inner radius is the radius in which the sound is just going to be 100% volume. And then the fall off distance is the interpolation radius between, okay, after, in this case, 400 units, it starts to go down in volume. At what point do we just not hear it at all anymore? And that would be 3,600 units from where the inner radius ends. So in total, that would be 4,000 units away from the player. I believe by default, what it does here is it uses the position of your player's perspective, so your player camera, not the player character. But we have our own footsteps, which are all well and good. Happy with that. And we have the enemy walking around right there, and we can hear him. And as he gets closer, he gets a little louder. I think in general, they are too loud. So let me set the volume multiplier as a whole for this sound cue down to something like 0.4 maybe. Because footsteps, while they should be present, also should be relatively subtle. And it's a pretty harsh sound that we ended up using here to begin with. So it's not the best footstep sound in the world, but we can now hear our character walking around. And from there, we can add a whole bunch more different stuff. We can add landing sound. When our character lands on the ground, we already have some code that runs whenever our character lands on the ground, because that's where those particles spawn in. We can also just play a sound effect. So that happens, I believe, somewhere. I really should organize this code a little bit better, but somewhere around here, maybe. There we go, on landed. We probably also want to play a sound effect. So we can literally just play sound either at location or 2D. And that is an important difference because a sound at location is subject to that attenuation. If you're not close to it, you're not going to be hearing it. It might have some spatialization to it so that you can find the source of it, the direction of it, based on whether it is left, right, or however many channels you have set up. A Sound 2D is always just going to play. It doesn't exist like in the world, it doesn't have a location, it's just going to play. So things like UI elements generally would play with a 2D sound because, well, there's no real need for that to be anywhere in the world. The thing though is that things that the player does pretty much always happen where the player is. So spawning that sound in at a location that is the same as the player's location doesn't necessarily make the most sense. So you might as well just play it as a 2D sound. And there we can just play any sound asset that we want. I have a not particularly good sound here, but it's the first one that I could find that we'll use for landing. Very, very much too strong of a sound. I also don't want that last little bit in it, I don't think. I just want this. So again, we just drag this in. And we could just play this every time like that, and that would kind of work. As we just had, there we have a sound effect when we land. Again, it is definitely not a fitting sound effect. We can turn just a single sound effect also into a sound cue, of course. You can just right-click any sound in your project, and we have a create sound cue, which obviously will create a sound cue. So SQ landed, that's going to be the sound cue that we use here instead. And there we can just use that one sound effect and still add a bit of a modulator to it so that we have a bit of randomness. And there's a whole bunch of different effects that we can add to this as well. As you can see, we can set up a decent amount of stuff with this if we want to. I prefer personally, when you start getting into this, to just move over to meta sound. And I don't think we're going to go through meta sound in this series, but I do plan on going into meta sound a bit more in the future in a standalone series. And as a whole, I also want this to be a lot quieter. So only like 30% volume probably. And ideally you would have more than one sound there anyway. But we have some sounds now. If you really want to be super cool and fancy about this, you will hook up the volume of this sound to the speed at which your character was moving before landing. So it also is louder if you were just falling a very far distance, you were falling very fast, compared to a very small little landing. And if we just open this Play Sound 2D, we have a volume and a pitch multiplier as well. And the wonderful thing is that the character movement component has a get last update velocity. That's going to give me the velocity of the frame before this one. So the frame before we landed, how quickly were we moving? And we mostly just care about the Z. If we just take the maximum between 0 and that, so that we never have a positive number, we always have 0 or something under. That way we know that we were falling. Then we change that to an absolute value, so that we're no longer working with something negative. And you can inverse interpolate this or whatever you want. The easiest way to just kind of deal with this is take this number and divide it by roughly a number that you expect this to be. I'm going to probably be falling at about 8 to 1200 units in velocity. You can just check if you really aren't sure what type of values to look for. Just do a print string on the Z velocity here and just run a couple of jumps back and see what values they give you. About 1000 there. If I just fall down here, was about 700. If I jump up this little ledge, it's about 500, 900. So anywhere between 5 to about 1200 is what I can expect. So with that, we just divide that absolute value by, let's say, 1000. Then we take the minimum float value between that and 1, so that we never do anything that is louder than what we intend it to be like. It's only ever going to be quieter. And we put that into the volume multiplier. Now it's also going to have different volumes depending on how far we were falling. And let's print string that to see what values that's spitting out and if that is anything that we would expect it to be. If we do this, it is 0. This is also 0. I did something wrong. Oh, this is, yeah, that makes sense. This also should be a min, not a max, because we're working with a negative number. We want to either return 0 or whatever negative number we were working with there. Don't want to use the max for that. And here we want to get the minimum between whatever this ends up being or 1. So if we try that again, then we should see that it starts working. we had a value of 1 there, but if we just go down a little bit, that was about 60%, and that's also about 70 or so percent. If I jump up here, you can definitely tell it's a lot quieter when I jump up somewhere because I don't land with as much force. I still think that as a whole, this thing probably is just too loud. Probably also just a bad sound effect. But you can play around with however you like to implement this, and again, we've added a sound effect that now also is a bit more dynamic in the way that it plays, informed by some gameplay information. Next time, what I want to do is I want to take everything that we've talked through in this section, which is a bit shorter than some of the other sections, because adding juice is about just doing stuff and doing it a lot, and just spending more time creating the actual assets than we have in these tutorials. There isn't that much to it. All this is about making something that is polished more than there being a billion different things to know. Particles and materials, there is a lot to know, and I do have dedicated playlists to both of those subjects because of that. But we talked about pretty much the most important things to spice up your game. I'm going to take all of that information that we've gone through and put it into effect in one singular thing that's going to need all those elements. And that is, we're going to make this dash less bad, because the dash right now is really, really awkward. Part of that is because the animation is also just a little awkward. But if we add a sound effect and some particles, a little bit of a camera shake, I believe that we can make this dash just feel a lot better. And that's going to be what we do to round out this section of the first game course. We're going to make that dash a lot better than it currently is. We may have a dash, but it kind of sucks. And the whole point of this section of this tutorial series is to add some juiciness to our game, to make things satisfying, to make things fun. And a part of that comes down to just improved quality over a bunch of the assets that we have so far. We've talked about particles, about cameras, about all sorts of different stuff. I want to put all that stuff together right now to just come together, make that dash a bit more interesting. First and foremost, I think adding a sound effect to the dash immediately improves that. So I have downloaded a file with a couple of whooshes in it, and I'm going to export those and put those into Unreal in a similar way that we did with the footsteps in the previous video. I'll make a new folder for that just to keep things a little more organized. Let's call that whooshes or something like that. And I will drag all those in, right click, and we'll make that into a single sound cue. And we'll call it SQ whoosh. Wonderful thing about doing that, by the way, selecting a bunch of things and making them into a single sound cue, is that it automatically just puts in a randomizer for us. Fantastic. That's exactly what we want that to do. Add in a modulator, which is going to keep with the default 5% margin to either side in both volume and pitch. And we have a whole bunch of whooshing sounds that we can use for our dash. Let's open up the player blueprint and start implementing that as a sound effect. Also get rid of this print string that we put in here last time. And let's see where our whooshing exists. I think it might be this jump dash. That's our dash animation. And we can either implement this as part of our dash animation, and I think we might want to, because our dashing doesn't start until some ways into the animation, I don't think. So we have this wind up first, and then here is roughly where we start dashing. So we want to add in a notify here. Add notify, we play that sound, and we'll call that whoosh, sound cue whoosh. Get rid of these notifications as well. And immediately, doesn't that just make it feel a lot better already? I think it does. It might also be good to have just a little bit less lead-in time to this, to be honest. So let's set the start time to something like 0.5, just so that the dash happens a little quicker. It felt a little unresponsive the way we had it before. So yeah, just like that. We didn't do anything about the animation here. We did shorten the lead up to the animation a bit, but just having that sound effect immediately makes it more believable that we are dashing. That's the power of having any sound at all. Let alone if this were really good implemented sound, that would be able to save something that is otherwise maybe not ideal. Sound is very, very important. I'm going to be adding a camera shake as well, just a small one. And we're going to be adding some particle effects as well. Let's add a new notify track so that we don't have everything just stuffed into one track. Add a notify. And here I want to add in a montage notify. These things are really, really useful. You can make custom notifies that do custom code for a thing that you need to use in a bunch of different animations over and over again. But for these kind of one-off things that I just want this to do one thing and I'm good just kind of programming that in to my player blueprint, these named notifies are really nice because I can give it as a name. Let's say cam shake. Copy over that name because we're going to be looking for this exact name in a moment. And then in our player character blueprint, where we play the animation montage, we have this on notify begin, and it gives through the notify name as well. If I pull over the notify name and I type switch on name, and then hook that up to on notify begin, I can have it do different things depending on the name of the notify that it gets given in. It's a really nice way of sending through information from an animation back into your blueprint. I can give the pin names in here. So by default, it's going to be called case 0, case 1, case whatever. I just give it the name camshake. And then whenever it receives a notify with the name camshake, it's going to be doing something. In this case, it will be getting the player controller and then play a camera shake. We'll start that camera shake on clients and make a camera shake that fits what we want to do here. And I'm going to animate this camera shake, just like we have before. What I'm going to do is I'm going to come up here into camera shakes. I will just duplicate the one that we already have. Camera shake animation, player dash, and open it up. I'm going to delete all of the terrible keyframes that we set up previously for this camera actor because this was not good. It's just it rotating around, right? We don't really want it to do that anymore. So delete everything there. Matter of fact, just delete the entire transform here. We're going to start from scratch. Add back in the transform. That's going to just give it to me at its default state, which is nice. And I'll add in one keyframe at the start here. Give it about 10 frames or so. And I will move back a little bit, maybe up a little, and then tilt down ever so slightly. So that is going to be the animation that we play. We'll stick with that for another 10 frames and then take another 10 frames to move back to where we started. So we have this as our animation, which is hard to see again because it places animation at world space 000, which in this map is nowhere. It's in the middle of an object, not ideal. Oftentimes it's good to make a specific map that you make these animations in that is just otherwise empty and just has your player like model standing in it, for instance, as a reference point, instead of doing it in the actual gameplay level where you end up with this kind of weird stuff happening. For now though, this is going to be the animation that we're going to be working with. Then let's also just duplicate this one, camera shake, player dash, and that will play our animation sequence that we made here. I want to do one more thing, I just realized, because I also want to increase the field of view of our camera, even if just a little bit. So let's take this and animate our camera component. And in that camera component, we want to animate our field of view, FOV. In this case, it's called current focal length because it spawns in a cinema camera. That's a small downside to doing it this way, is because we're doing everything now based on a cinema camera, while our player character is usually looking through a normal gameplay camera. And there's upsides and downsides to both types of cameras. Cinema cameras are usually constrained to the aspect ratio that you set them up as. So they might end up conflicting a little bit if you want to play it on a widescreen monitor, for instance, or for whatever reason, a more square ratio monitor or anything that's not just your usual 16:9. And they have a handful of differently named settings. In this case, instead of field of view, it uses the current focal length. And we just animate that focal length. You animate the value down if you want a wider field of view, whereas field of view, you, well, animate that up to get a wider field of view. Let's animate this to 25. Again, I'm going to just copy this keyframe over here, make it last for 10 frames, and then make it go back. It's kind of hard to see what this does because, again, we don't have a real good reference point here. It's kind of annoying. Back in the player blueprint, we need to give in this camera shake as the one that we want to play. So that'll be the player dash. And before we move on, let's test if that actually plays. We can see it very much does. It does do the wrong field of view though, which is not ideal. I'm going to just hide all of these components real quick so that we can see what we're doing while animating this, because it's otherwise really annoying. Okay, yeah, it does go wider in the field of view here. As you can see, if I pull this back, it becomes wider. But because the settings between the cinema camera components and the gameplay camera components are so mismatched, it becomes a little bit weird to work with this properly. So you might need to just kind of tweak about with that and just kind of figure it out. We also have the blend in and out time set to something kind of weird. So maybe set this to just 0.1 and 0.1 instead. Right now, the blending takes up half a second of a total 1 second animation. Maybe 1 second is also just a little too long. And honestly, maybe we don't even need to animate in and out all this stuff. Maybe all we need to do is just set this to be the adjusted positions. And then have the blending in and out of the camera shake be the thing that interpolates from 0 to the new position, from the new position back to 0. That might end up working out a little bit better because it's a little shaky, it's a little weird the way that it is now. Let's see if that maybe... that feels a bit better. It's definitely too long. We definitely need to make it shorter. And this is just the type of tweaking that you're gonna end up having to do. If this feels like I'm jumping back and forth all the time, it is because I kind of am. Let's see what this feels like if it is just 15 frames long, only half a second. We can probably check that against the length of how long this takes. This takes from 0.28 to 0.45 or so. So that's about 0.15 seconds. Half a second might still be a bit on the long side then. We do need to take into account the fact that it is interpolating in and out a little bit, and those both take a tenth of a second, so about 3 frames. That means that from here to there, and then from there to there is all blending. But we can probably have, what about 3 frames of blending, then 5 frames of being in this camera state, to call it, and then 3 more frames of blending. So we have a total of 11 frames of length. That feels like it might work. And I feel like the blending back also could do with being a little longer. It's a little harsh blending back. There's probably a reason that the blend out time was longer to begin with. So let's set that to 1/4 of a second. That might start overlapping with it, but that ends up feeling pretty good, honestly. A little better than I imagined it. And between the animation for the camera now and the sound effects, this dash is starting to feel like something. It's a little jarring, maybe. There's a fine balance between something feeling impactful and something feeling jarring. However, we probably still do want to add in one more thing, and that is some pretty nice looking particles. Just something that shows, hey, we're dashing. Movement lines, essentially. And for that, well, let's just make literally movement lines. We're going to make a Niagara system, and we're going to work off of a existing emitter to start with. And I think that one is going to be minimal. Minimal is a pretty nice one to work off of usually. Let's call that NS dash. Because what this allows you to do is have something that is not filled in at all, but does have the emitter state already filled in, an initialized particle, comes with a sprite renderer, all that type of good stuff. I don't think we're going to be using a sprite renderer though. We're going to use a new type of spawner, and that is spawn per unit. This is instead of spawning a bunch all at once or spawning a certain rate of particles per second, this is going to spawn one particle per distance that the emitter or the system is moved. So if we just put this into the world, we can see that if I just don't move this at all, nothing spawns. Only when I start moving this, every X amount of distance that it moves, it's going to spawn in a particle. Then that particle can do whatever that particle needs to do, whether it be have gravity, have some type of force applied to it. But this, obviously, as you can probably imagine, is really good for creating these type of trail effects. But it's also kind of ugly having all these separate circles for that. So instead of doing a sprite renderer, what we'll do is we will make a ribbon renderer. This is just a line that will go from the first particle that it spawned in toward the second, toward the third, toward the fourth, and all the way to the last. And with that, we create this. Literally just a line that goes through all the particles that we have. Now we do want that ribbon to probably be a little bit less thin, and we want the particles themselves to definitely don't exist for 5 seconds at a time. Half a second, maybe even just 0.1 seconds is probably more than plenty enough. But now that we're in initialize particle anyway, we can set up the ribbon attributes and we can set the width to being just a direct set of, I don't know, 15. The downside to these spawn per unit particles is that they're kind of hard to preview. Because of course, within the preview window here, it's not going to be moving. So you do need to tab out over into your actual world. Just move it around a little bit and see what it looks like. In comparison here to our player character, what does this look like? It looks like it's a bit short still. So probably want the width here to be significantly bigger than it is at the moment. Let's go to 55 maybe and see what that's like. It's a little bit more like it. And much like we did before, we can just add in some notifies into the montage here to start and stop that particle system. We'll add one more notify track, right click into it and add in notify states. Unlike all the notifies that we've done so far, which are a one and done, it just runs and either it does something or it sends a signal for a blueprint to do something. Notify states are notifies that have a start point and an end point and then, well, in between. We're not going to really worry too much about the in-between right now. All that we care about is that this is a notify that has both a start point and an end point. And we have a montage notify window, which is the exact same thing that we had before here with the camera shake, but this just gives us, well, a window that also gives us an endpoint. And we'll call this the dash trail or something like that. It really doesn't matter what we call it, we just call it something. Now that we have that set up, we can go right back into where we play that animation montage and just on this switch on name, add one new pin and name that our dash trail. Now, when this montage plays, whenever it starts and notify begin, if it's the cam dash thing, it does this one. If it's the dash trail, it does whatever we put into here. Then on notify end, it also can give through the name of the notify that just ended. Of course, in our case, we only have the dash trail as a notify end because no other notify windows exist. Still, it's good to just make sure that there's a switch on name here. It's going to end that dash. But now, how do we do that? How do we use that particle system and activate it and deactivate it based on that dashing? That's where particle components come in. So far, we've only done particles by just spawning them in, and that's fine, and it's not really that big a deal to do it that way. But a particle system that belongs to a specific actor that's going to need to be activated a bunch of times, especially attached to that actor, like we have right here, you can add that as a Niagara particle system component instead. And I'm just going to add it here as a child of the capsule component. You could add it as a child of the mesh instead, and maybe even hook it up to a specific bone, like somewhere in the spine for our character. I'm going to do that for now. And we'll just put in our Niagara system for dash. And because we had that asset selected in our content browser, it automatically put it in there. That's why you can see that it already has Niagara System Dash. If I didn't have that already selected, it would just be an empty value, and I would need to populate this like that. We can set up a whole bunch of stuff. If we have any user parameters, they would be available here as well under the user parameters, just like we've seen before when we just spawned them into the world. The most important thing here is whether or not it should automatically activate. In this case, I wanted to not automatically activate. I only wanted to activate when I start dashing and then deactivate when I stop dashing. And that is why we have these two switch on names connected up to display montage, because we can pull in this Niagara System for dash, and we can just activate like this on dash trail. And then we can also deactivate when we end it. It's probably also a good idea, just to be sure, that whenever we complete it or we are interrupted, we also manually deactivate this, just to be sure that it doesn't get stuck in an activated state. So in here, when we start setting our gravity scale back to what it usually should be, we also just make sure to deactivate the dash. If it is already deactivated, that particle component, this doesn't hurt anything. But if somehow this animation montage got interrupted and this end notify, we never get to this point, that would just keep that particle component infinitely activated. And, well, that's not really good. But with all that set up, we don't have a infinite trail behind us now. But when we dash, we do have that trail like this. It's always facing toward the camera because that's how the particle is by default set up. But you can set this to be a custom facing direction, which will use the particles.ribbon facing property to decide which direction it is facing, or use the side vector, and that uses the particle ribbon facing as the side vector. So this will point it in the direction of whatever vector you give in. This will pretty much just rotate it 90 degrees from that vector instead. And you should be able to set that here in Initialize Particle with the ribbon facing mode. If you set that to direct set, we get the ribbon facing vector. I'm just going to stick with having it face toward the screen always, because that's much simpler. Although, especially with these thicker ribbons, it does sometimes feel a little weird if you look at it from the top and then also from the side. And one way to fix that would be to not have a single one of these, but just have a bunch of smaller ones instead. So you can just copy over a couple of these, and then in Initialize Particle, we just give it a position offset and give one of them like 50 units up and like 10 units across. One would be minus 15 units across, maybe like 20 units this, and then minus 17 down. And you can just add a whole bunch of these to just make a whole bunch of smaller lines like this. And that just makes it a little bit more believable when you're looking at it from different angles. Because it's mostly when those ribbons become very wide that they start being a bit of an issue. And we can even, in theory, actually make those random. Because we can just make a random range vector, and we can say, well, we want this between anywhere like minus, let's say, 30. The y doesn't really matter that much, because the y is the forward and backward axis here. Just a little bit of a difference there at minus 10. And then this would be anywhere between 50 units up or down. And then we just do the positive versions of those everywhere in here. Oh, and this needs to be negative 50 then. And we just copy that over and put that everywhere in Initialize Particle, paste that down instead. So we just paste. And honestly, if we're going to be doing that, we might as well just copy paste the image as a whole. I don't know, something like 9 of these will probably be good enough. Don't go overboard, because you still are spawning in a lot of particles. But let's see what that looks like. That's maybe a bit much, isn't it? Yeah, that seems like maybe a bit much. There also is the issue that now every particle is spawning entirely randomly, and we don't want that. We want every particle to spawn at a given offset. So we just remove all of these, and we're going to make one random value that we generate on emitter spawn instead. And we've done that before. We set or make a new parameter, And that parameter is going to be a vector. And that vector, we will just, let's see, do that random range vector exactly as we did before. So -30, -10, -50. And we can tweak this to a hard content at a later date. And then when we initialize the particle, instead of every particle individually getting initialized with a random offset, we can just use the vector that we made here. And now every particle per emitter is going to have the same offset. I'm just going to show you it with one of these now. It still is a straight line. It's just going to be a straight line that starts at random locations every time I do it. And as such, we just make, again, like 9 of them probably is good enough. Just copy this over a handful of times. And we have our little speed lines. Of course, that does make the possibility of what you saw there a moment ago, where they do all spawn more or less at the same location, because randomness will just do that, but we have speed lines. Sweet. Now that said, they do kind of start out of nowhere, which we can do a whole bunch of stuff about in the particle system itself. We also can just move the particle system a little bit forward. I think that probably solves most of the issues that we have with that. Yeah, there we go. And with a sound effect, with a camera shake, and with some particle effects, even if it is very, very simple, all of them, our dash has dramatically improved over the course of this video. Now, is this ready for a AAA Steam release? No, obviously not. But hopefully this shows you that with just a little bit of work, you can polish up a thing that felt and looked really quite rough before into something that is immediately a lot better. If we fine-tune and tweak and develop all of these aspects a little bit more, even better, more polished camera, sound effects that do a little bit more. I quite like the sound effects as they are right now, to be fair. And particle effects that just have a little bit more going on for them than this, even though this is a really good start, that would even more increase what we have going on here. There is a bit of an 80-20 rule here, which is you get 80% of the way there with just 20% of the effort, but that also means that the last 20% of the results will take 80% of the effort. What we've done here is that 20% effort to get us 80% the way there, to get this looking and feeling actually really good. It's going to be multiple times the amount of work and skill required to get us there. Next time, we start off the final section of this very, very long series, where we take everything we learned here and in the previous sections combined, and pretty much do a large version of what we did here, and have everything come together into making a single thing. That's going to be a boss fight. We're going to make a character, we're going to animate the character, we're going to program the character, we're going to sound design, particle design, all that type of stuff in the next section of this course as we round out making our first game in Unreal Engine. And a very big thank you to all my Patreons. You can see them on screen right now. If you want to help support the channel or get any of the project files in any of my tutorials, there's a link down below to the Patreon page to support me, or alternatively as a YouTube member. With a special thanks to my Cave student tier supporters Oiku and Earl Monseville Erno, and my Cave Digger tier supporters Mauricio Ferias, Cheng the Dude, and Joshua Mater.